Okay, I think I have everything working. I am playing around with some options for displaying things in the stream. Oops. Sort of hoping I could get it straightened out so that yeah, it looks like it's working. So hotkey buttons to flip between the chamber view and the live camera view. Hey Del, and Pacific Plankton, and Anarchy Kitchen, welcome, and Kalathon and Charlock, hello. Let's see. Right now we are looking at. I was just sort of zooming around in the slides a little to see, or the stubs a little to see if there was anything good, and to make sure that the additional rinsing that I had done improved the quality of the samples. So we should be able to see a little bit more. There should be a little bit less clay in these samples. There's a nice clean view of an isthmia, for example, just one valve with the girdle bands attached. And hopefully if I zoom in kind of close here, we'll see not a lot of clay. You can kind of see into the details of what we're looking at. We're still quite a long distance away from the sample, so I haven't moved it up yet. I also wanted to make sure that the materials that I had from Clear Lake were going to turn out okay. So I think we're going to start with those. And Addie's in the lab right now, but I think she'll also be coming over to join the stream in a bit. So I've got my mask ready for when she gets here, but I didn't want to demand that she come do this instead of work on her actual samples, which is what she's working on. So I thought I could zoom around in these a little, try to see what's here, and then maybe when we get when they sort of exhaust that, we can move over and look at some of the material from San Francisco Bay that I prepped for today. I got some more samples from Pacific Plankton as a Christmas gift, and those are currently on a hot plate filled with nitric acid being digested. And once they're finished being digested, I'm going to have to rinse them a few times, and then we'll prep those probably for Saturday. I'm not sure what's going to happen Saturday, but that's probably be our first stream in the new year. And we'll look at some more of those San Francisco Bay samples, I think. So I also probably will prep some of the live material, unprocessed material. I still have to rinse the salt water out of it and get a lot of the clay out of it if possible. So I started working on that today, and we'll see. Hopefully we'll get it arranged. So the orange makes me look like I just did a prison break. Well, do they have cool octopus shirts in prison? If so, sign me up. I'll go to prison for a cool octopus shirt. El Simp, hello. How you doing? You've come for my soothing voice. Well, I'll try to keep it soothing. And Andalore, welcome as well. And yeah, this is a bit of a long distance collaboration between Pacific Plankton and I. She periodically will send me samples, and then I will prep them for the SEM. Here's Addie. Hiya. I got your samples in.
Really?
Yeah. So, let's see. I was just sort of poking around at them and trying to see what's here. And the stream is running. So this is Addison. She's not visible to you. So if I turn it that way, she will be. Get around my Coke bottle. Let's see. Yeah, they can see you now.
Hello.
And Addison is a master's student now, working with me on research from Clear Lake. Which state is Clear Lake in?
Iowa.
Iowa, right. I knew it was something with an I in it. I just couldn't remember which one. So from the Midwest, and these are some materials that Broxton Bird, who's a collaborator of mine, who's at IUPUI, collected from cores. So, and Addie has started looking at this stuff in the light microscope. I don't think we've prepped any of the samples for the SEM before. You can see there's still a little bit of clay sort of clumped onto it, but I think we can see many of the diatoms well enough that we can still manage with this. This Alicocera, for example, is just coated with clay, right? So if we wanted to get rid of that clay material, which I usually do for the scanning electron microscope, we would take this and probably put it into the ultrasonic water bath for a little bit, just maybe 30 seconds or something. Basically, it'll vibrate and shake the diatoms and get some of the clay off, and then rinse it a few times. So we'll shake it up, we'll get the material all sort of agitated, and then let it settle. And if we let it settle for like maybe 5 minutes, what will happen is the diatoms and all the coarser particles will settle to the bottom, and the clays will still sort of be floating around on the surface. And then we just rinse it, basically, vacuum it out, and it will get rid of all the clay, at least in theory. Some of the clays are probably stuck on there because these were collected from benthic, or not benthic, from sediment samples. And so they're going to have a bit of the mud from the surrounding material sort of stuck on them. And hopefully if we sonicate them a little, it will get rid of it. But you can kind of see the effect of the clays, right? So we don't have nice clean views. But this is a Criticula that we're looking at here, this large diatom. It's a Benthic Diatom. And it's probably Criticula cuspidata. I don't know, something like that. And then there's a Gomphanema. You can see here. Everything we're looking at is basically just the surface. So if there's a lot of clay covering the surface, as a result, we can't really see the structure of the diatom super well. And you can see that in here. There's little holes right here that we would normally see on the diatoms. And with the clay sort of coating over top of them, we can't really see a lot of those details. And then there's some clay sort of landing on top of all of this stuff, really. So I was kind of anticipating that would happen, because, you know, normally when we look at stuff, we rinse it a few times to try to get the clay out. But there's always a chance that some of this stuff basically won't be covered with junk, and we'll be able to get at least some clear views. So here's a amphora that's partially covered in clay, but you can see some of the areoles and the openings on the structure on the valve face. And then, I mean, I can still identify them even with a little bit of clay on them, which is good. Most of what we see on the sample is actually Alicocera, these little sticks of Alicocera that are here. They live in colonies, and some of them might be clean enough that we could actually see some of the details. But a lot of what you're seeing is basically just the girdle bands and then clay over top of the girdle bands. So you won't get a lot of the really pretty pictures out of it when it's in this sort of state. I think you could still ID them. You still sort of see them by shape and know what they are. But I think we'll probably need to sort of do a couple of rinses and see what we can get, try to get some better views. Here's a nice Stephanodiscus. So I don't know what the species is. Do you remember any of the species that you have in your samples?
I've not seen a lot of Stephanodiscus.
Yeah. So
there's a lot of smaller ones.
Yeah. This is actually a pretty large one.
Yeah, I've not seen a big one like that.
Yeah. Well, that's another thing is sometimes with the SEM you'll see a few things and you'll be like, I didn't really see that, because it's pretty uncommon, right? It's not like we're seeing them all over the place.
Yeah.
But, like a random thing might sort of plop down in one of the samples. So like most of what you would see if you were to count this would be Aulacosira.
Mm-hmm.
And then it's a nice pretty Cerarella. And some Pinularias. Oh, and that's a nice one. You can see that most of the clays have come off of it. And we can kind of zoom in and take a look at it. There's also, that's a Chrysophyte cyst right there in the background. The Cerarellas, some of them have these like really cool sort of spiny coverings on them. So they look really like, hardcore, right? They've got the little spines all over the surface. And this is one of those questions, like I don't really know why would diatoms grow little spines like that? I don't imagine that there's things that are trying to eat them that a tiny little spine like that would really do much to sort of protect them from, but that's the way people usually, when they see spines, they usually, sort of ornamental spines like that, they usually think, oh, they're for the protection of the diatoms, but I really don't know why or how that would help a diatom like this. So I'm not saying it's not for their protection against things, but I'm just saying that I don't know how that would help protect them very much. I mean, if you're going to bite a diatom, your mouth has to be pretty big, and these little tiny spines probably aren't going to deter you much. So, but they're kind of cool, and it's nice that we can resolve them. Or we could if I had it in focus. So I mentioned this is a Cerarella, which is a benthic diatom. Usually they're found living on muddy surfaces or substrates, like on the top of them, and or sandy substrates. And they're raphy, which is a little slit in the valve surface that goes through into the interior part of the diatom. Is circumferential. In other words, it goes around the outside of the valve rather than through the middle of the valve, which is where most of the raphies are usually on diatoms. And they use this to crawl around. And I don't think we quite understand exactly how diatoms crawl around yet, but they use this as their tool for locomotion. And the cool thing about Cerarella is, so the top valve is this one, and then there's hardly any girdle bands in here. And then the bottom valve is this one, and you can see that what happens is like a tank or an X-wing fighter or something. Its raphy are all out on the outside edges, so no matter which way it lands, it always has a way of sort of crawling and having its raphy attached basically in 2 points. So they're like little boxes basically, and as a result, they can crawl all the time in every direction. So it's a huge advantage for them. It means that they're probably highly mobile. So most people don't think algae can crawl around, but diatoms are a type of algae that actually crawl around. And so that structure actually allows them to be able to crawl around very easily. So let's see. I'm going to look at the comments. Greetings, Addison. Hello, Addison. Who's joined me today? So covered that. Yeah. And it's, yes, an X-wing like diatom. So, and then this thing up here in the corner is, that's hiding underneath the diatom, that's a round thing, is a Chrysophyte Stomatast. And oftentimes for temperate lakes in the US, in the wintertime, the Chrysophytes will encyst. So they'll create a little ball to crawl into, and then they'll use that to basically live through the winter or something like that. And they fall out of the water column for the most part. They're not active. They're just like a hibernation-like state. And there's a hole on it somewhere. We can't see it because it's hidden, but I could tell that it was a Chrysophyte cyst because it has ornamentation on it. So this one's got these little sort of stripy, like fins on it. And some of them have almost no ornamentation. They always have a little hole somewhere, and they're basically shaped like Christmas tree ornaments without the hanger, right? So there's one, and I think this one is probably a chrysophyte, but you add microspheres to these samples, right?
Yeah.
So if it's something that's about 5 microns in diameter and it's round like that, it could be a little particle that we added to try to figure out the concentration of diatoms or chrysophytes or whatever to the amount of sediment that we analyzed. So looks like we got some big clumps in here. And a bunch of Alicocyrus still. There's some bigger ones and some sort of skinnier ones. And I thought somewhere I had seen, oh yeah, up here. There's another one of these Cirrella, a big one. This one I don't think has those spines. It's got a slightly different sort of structure. You can see it's all full of clay on the surface. And then this big diatom right here with the big chambers it's laying on its back basically. So its valve face is open to us. We can see inside of the diatom. And then these little chambers are typical for Pendularia. And if we were to zoom in on the chambers themselves, we might be able to see the areolae on the valve face through the openings. So they have a bunch of little tiny areolae that are inside here. If the focus is pretty good, and it looks like we got a decent focus, and we zoom in, you can see there's a bunch of little holes in there. So on the inside of the valve are the actual little areolae holes. You see a little like kind of porous structure in there. So in the light microscope, you never see those, right? You just see these big, the striae themselves are the costae between them. And in Pendularia, as I mentioned, they're chambers. So, and also Calanice, but you can see that there's little tiny holes on the inside of those, and those would be on the outside of the valve, right? So. So it looks a little glitchy. That's just because when I zoom in and out, the SEM has to redraw the image across there. So pretty cool. And I see something here. It looks like maybe it's a Cnidium and another giant Pendularia. And this looks like maybe a Encynema. No, maybe an Encynema. Yeah, we'll see. Probably when we rinse them, we'll get a little bit better view of a lot of these diatoms, and then we won't have as much clay blocking our field of view. So, can you talk a little bit about what you're doing on the project with Clear Lake?
Yeah.
So why don't I, do you know how to use, have you used the SEM before?
I haven't.
Not at all?
No.
Okay. So I didn't know if maybe you did stuff with Jim or not in one of his classes.
I watched him one time do it.
Well, you can actually run it for a little. I'll let you do it while you're trying to talk. That way you have to multitask. So all you need to do is middle mouse, the wheel. If you click the wheel, that becomes the center of wherever you're looking. So if you wanted to look at that thing, you just click on it with the middle mouse and then it moves to the center.
Okay.
So if we wanted to look at this thing right here, it will move to the center. And then this top wheel is zooming in and out. So it's another one of those larger steps. And it's got clay all over it. And then you can use the bottom wheel to focus a little bit.
Okay.
So, and then simultaneously talk about your research.
Okay. Putting me on the spot here.
Well, this is the challenge.
So let me make sure I have this right. So this is like
In and out.
in and out.
Yep.
Okay, and then let's
And then
just
that one's
zoom.
focus. So once it's in focus, you shouldn't need to mess with the focus too much again.
Okay.
But you might want to change it for the, where you are.
Okay. So what does this do?
The middle mouse moves it.
Okay.
And then if you roll the mouse wheel in and out, it changes the speed. So slower speed gives you higher resolution images and faster speed lets you move around.
Okay. Yeah, I've never done this before, so.
Yeah, it's okay.
Okay, so as Dr. Stone mentioned, I'll be working on Clear Lake, and that's in Iowa. And so I guess I'll just give a little bit of my backstory, maybe.
You can take your mask. I'll move back.
Okay. Good, because I don't like talking in this
Then they
thing.
can see you.
Yeah. So anyway, yeah. So I'll be working at Clear Lake. And currently, I think I've got about 200 and maybe 220 samples or so altogether I've got to look at. But yeah, so I'm a master's student, and I'm doing what's called the 4-to-1 program. So try to zoom out here. It's kind of awkward because I'm trying to figure out how to do this as I'm streaming.
Just pretend they're not. Pretend you're just talking to me.
Okay. Okay. So, anyway.
You can also just leave it on there and talk for a little bit.
Yes, I might do that.
I feel like you have to address everything at once.
So, okay. So I'm doing the 4-to-1 program, and that's a program where it's an accelerated master's program. So I'll be able to get my master's in a year, whereas most of the time it takes people 2 years. So I'm trying to really get busy getting stuff done because with COVID and just everything that's happened, I kind of feel like I've gotten behind the 8 ball. But as of right now, the running title for my thesis is the impact of hydroclimate variability on diatom assemblages of Clear Lake, Iowa. And so I'll be looking at diatoms from 2 different cores at Clear Lake and assessing how the different shifts in the dominant species of diatoms over time. I think the record goes back maybe 2,000 years or so. So over 2,000 years, roughly, I'll be looking at how different dominant species have changed over time. And that will give us a record of, I guess, how hydroclimate has also changed through time. So this is kind of important work because we don't really have a lot of high resolution records for the Midwest. A lot of what we have are tree ring records, and they don't go back very far because of a lot of clear cutting that happened. And so lake records offer us really interesting records because they're everywhere, basically. And they tell us a lot about what's going on in the terrestrial environment. So we can use different proxies within lakes and look at how past hydroclimate has changed through time. So I'm really excited. I'm still learning all about diatoms, and I was fortunate enough to take a class last semester with Dr. Stone where we learned about diatom taxonomy. So this is all just really new to me, but the more that I learn, I think the more interesting it becomes. So I'm pretty excited.
It would be bad if we went the other direction.
Yeah. I was kind of nervous at first because this is just something new, obviously. But like I said, just the more I learn about it, the more I want to learn. So
there's a question from Bluebird22, which is, do you get to collect your own samples?
So I do not get to collect my own samples. They've already been collected for me by Dr. Broxton Bird from IUPUI. So I wasn't involved in that process at all. I think it was May of 2017 that they were collected. So I just kind of have them, what's it called, where they're split out from split.
Yeah.
So,
Subsampled,
yeah,
maybe?
subsampled. And right now I've got the first 80 samples processed completely where they're into microscope slides. And I'm working on counting. I'm going to start that here in the next couple weeks. And so then the rest of my samples I'm working on processing right now. Actually, just came from doing that.
Like just came from doing that.
Yes.
So we took some of those samples that she'd already processed and just put them onto little aluminum stubs for this, so we can take a look at them. And then I think probably what we'll do sometime this summer, provided that we still can operate over the summer, is do a little bit of coring so that you can get that experience, so you can know how to do the fieldwork component. Because I actually think it's a interesting process.
Mm-hmm.
My preferred approach to coring is actually to core on frozen lake surfaces, and not when it's super cold, but when it's cold enough that the lake is completely frozen and there's a nice thick layer of ice. It's actually a pretty stable platform to core from, and it's actually a lot easier than doing it from a boat.
Yeah.
Where you have to worry about all your stuff falling in the water and losing it, or I mean, you can still lose stuff into the ice, but if the ice is nice and thick, then you don't have to worry about it. You just get an ice cutter, cut through the ice, you got a hole, and then basically you can just take your core through that.
Yeah.
So the problem with Indiana is it never gets cold enough anymore to really get like a thick layer of ice such that I would trust walking out onto it.
Yeah.
We have occasionally had some really cold snaps where where there was like a 3 or 4 inch thick layer of ice, and I felt comfortable putting students out on it. But I think normally it's a bit much to put students in that sort of position, and I like to be extra safe. If you've got an inch of ice, you're fine, but I like to make sure it's several inches so that I'm not fishing a student out of the water or calling the fire department.
Yeah, that wouldn't be good.
Bluebird says, is it more difficult to get your own samples because of COVID, since you have to travel? Well, I'll answer from my perspective. The university will not let me travel.
Mm-hmm.
So currently I don't have permission to travel for my job, and that is COVID related. So like if we were going to try to collect samples for a new project, or if we wanted to go back to Clear Lake and look at some stuff, right now the university would not allow it. So we need some permission from the university in order to go out and be able to do that. So if you double click with the mouse, the other button, sorry, the main button, yeah, it makes a little box, and now it only scans inside the box. And you can focus inside the box, and also it only scans that part, so it's a little bit easier to get the focus right.
Okay.
And if you double click again outside the box, it puts the whole thing back into focus.
Okay, cool.
Whatever focus you had at that. Also the magnification changes to whatever you had that one at. So that's just a top view of an Alicocera, and you're looking, well actually you're looking at the inside of the diatom, so that's the a view from the bottom. Its face is touching the stub, right?
Mm-hmm.
And then so that little inner ring that you're seeing,
This here.
Yep, is the ring least. So it's like a little shelf, or like a band of silica, a narrow band of silica that lines the inside of the valve face where the two valves join.
Mm-hmm. Is it possible to tell what they are from just the top?
Generally not. So Alicocera taxonomy is mostly side view, girdle view, because that's the way they typically land.
Mm-hmm.
You could potentially, if you like did a study on your own of looking at the girdle bands, you probably could use that to help you figure out which one you're looking at. But generally speaking, when I have a view like this in the light microscope or the SEM, I just put Alicocera SP, And then, I mean, I can't do any better than that.
Yeah.
Without knowing for sure. Or if you only have one species of Alicocera, then it's pretty obvious
Yeah.
which one it is. But typically, other than using the size, like the diameter of the valve, you're probably not going to be able to figure out which species it is.
There's tons of Alicocera in my samples.
Yeah. Well, it's a positive because it's easy to count when there's a bunch of Alicocera. So.
Yeah.
Because usually there's a whole bunch all at once. So let's see. We got some new followers while we were talking. Oxflarian, Steve Heeman, and Raymond 1. So thank you for
Hi,
those
everybody.
follows. Do you know which one that is?
I should know the name, but
I
I should know the name because I have a lot of these in there, and
Well, it's not a quiz. Can you zoom in on it?
yes.
I think it's a Stereonella.
Yeah. That sounds right. Figure out how to do this.
So typically with the Stereonella, they look like a Q-tip. Except
That's
for
what
one
I was
end's a
gonna
little
say.
bit bigger than the other, so they're asymmetric. And then that's a little clump of things that are below it. Maybe they're chrysophytes?
Yeah.
Although they look like it could be a little clump of microspheres, actually.
Yeah, that's kind of what it looks like.
Yeah. So probably too much clay on it to really see much of the detail for that species. If there's enough of them when we clean them up, they should look pretty good. The external views usually look a little bit better for Stereonella than the internal views.
Is this just a girdle band, or is that the whole thing?
That's the whole valve.
Okay.
It's just an internal view of the valve.
Okay.
It's got clay on it, so you can't.
Yeah.
Like I said, you can't really see a lot of the detail, but maybe it's broken. I don't know.
Yeah, it kind of looks like it is.
A lot of times the Stereonella, because they have those really long, skinny shape, like sticks or Q-tips or whatever. There's organisms that are trying to eat them, and they will break them.
Oh.
They can actually like manipulate them enough to break the valves, and so they'll snap them so they can eat them a little bit more easily. So if there's a lot of predation, you'll get a whole bunch of little broken ones like that. So that's just a girdle band, I think, for an Alicocera, or potentially it's just a broken Alicocera. I think it's Alicocera.
Yeah, it looks like it is.
So if you zoom way out, you might find some things that are a little bit more clean, or maybe some interesting chrysophytes or something. I don't know. And you can also just kind of browse around by middle mouse button and kind of roll around the screen and see if you find anything. I'm not trying to tell you to do it. I'm just
Yeah, I just don't know what I'm doing, so it's helpful.
So like if you go up and look at this one maybe.
Okay.
So there's a bunch of those. I'm not sure if that's a pinnularia or a navicula.
Yeah, I can't.
Until we get a little closer and I can see the areolae. So if it's a navicula, there'll be little slot-like lineolate striae. And if it's a pinnularia, it'll be like the one that we just saw that has just little tiny holes. And I guess this is actually a navicula. Can you zoom in on one of the open areas? Yeah, right in there. Yeah, it's definitely a navicula. You can see the little slot-like openings.
Wow.
It's always the getting used to the controls. So
Yeah.
double click outside the box anywhere.
Okay.
And then you can zoom in with the top mouse wheel. I promise, after you do it a little while, it just becomes like second nature.
Yeah.
You don't have to think so much about like, what am I supposed to do? But yeah, you can see on this, in the little openings there, are the striae.
Yeah.
So, and then the little tiny holes are the areolae. And if they're in little bands like that, then we're looking at a navicula. So even though the shape and the size of this one is kind of similar to the pinularia that we saw earlier, the to get rid of the boxes, double click. Yeah.
Okay.
And that's probably a chrysophyte.
Okay.
It looks like there's a bit of the aperture sticking out.
Yeah.
Right. Actually, it's the one sticking upward.
Oh, this here?
Yep. I think that's a bit of the aperture. I don't know what that bump
Yeah.
is. So.
Okay. Zoom back out.
Let's see. Some questions. Somebody just wrote, "What is that?" I don't know how to answer that. It's a diatom, I think. What are the tubes? Oh, the tubes are Olicosyra. The tube-shaped things are Olicosyra. It's a type of diatom. Everything that we're looking at, except for the ones that are little balls, are probably diatoms. Little balls are probably, like little round things, are probably chrysophyte cysts. Some of them are fairly large. I think they can be upwards of maybe 50 microns in diameter, and smaller than 5 microns for the really small ones. Raymond 1 asks, is there a stream schedule? If not, when is the stream usually on? We usually stream on Wednesday and Saturday from 1 until 3. Although usually my idea of 3 goes to 4 because I get interested in what I'm looking at. So we'll probably do about an hour of just Addie and I looking around at Clear Lake stuff, and then I'm going to jump over to the San Francisco Bay stuff around 2. But we should be back on Saturday looking at some more stuff from San Francisco Bay. And one of these days you're on the focus knob, yeah, okay.
There we go.
One of these days we're gonna look at some lizard stuff, like actual lizards, in the SCM. There's another pinularia down there, I think.
This one?
Yep, I think it's a pinularia. It's the middle click. Yeah.
Yes.
It's such a weird combination of things, but you just get so used to doing
yeah.
it.
Yeah, it kind of looks like pinularia.
I don't mean to put you under pressure. First time using it on a stream in front of people, but just forget about them.
Okay.
That's what I do.
Not even there.
Yeah. I'm just answering questions from outer space. Oh, what time zone? It's Eastern, U.S. Yeah. Sorry. Those are all good questions.
Let's see if I can get this in focus.
You're doing fine. Don't worry.
I'm learning.
Yeah. It's fine to do a learning stream, in fact.
Yeah.
For people who've never seen a scanning electron microscope or seen one being used, I think that one of the things that's nice is somebody who's never used it can sit down at it and relatively quickly get through the controls with a little guidance.
Yeah.
It's hard to break this particular scanning electron microscope, especially if you're just using the mouse and that panel over there. It's really hard to do anything wrong. So, other than just get it out of focus, there's not really a whole lot you can do that will create problems for yourself. If you use some of the higher end controls, you could potentially break it, which is why I'm still here.
Thankfully.
Yeah. We'll probably do some training on the SCM. But if you just sit with me and do this a few times, it will be super easy. They don't always have to have streams attached to them. So,
okay.
If you feel pressure from that. Yeah. Kevin's text says, "Don't worry about us. We are just taking notes on how to use the SEM." And Andalor says, "You're doing great, Addison."
Thanks, guys.
The audience also then gets to sort of see how easy it is to use it.
Yeah.
And I can kind of explain the controls of it. Got a text message from Chad, and then he wrote back, "Ignore that, Cassia was on my phone." Getting messages from Chad's daughter, who's 4. So, also if you want to maybe try jumping over to the other stub.
Okay.
That's also relatively easy to do. So with the carousel, all you do is click on number 1, that will be yours, and it will move us to that stub immediately. And maybe there's some stuff here that's a little bit cleaner. You never know. Or some other things that we haven't seen. So, and you can move back and forth between them very easily, which is one nice thing about the test scan SEM. It's another one of those large steps. That one looks like it's a little bit dissolved. So, like the whole valve isn't there.
Trying to focus it. I have a lot of the really small stuffs in mine, so I'm surprised that they're
probably hidden right now in the clay. You know, there's actually in the bottom left-hand corner, there's a chrysophyte with the aperture. You can see the aperture on that one. So, as an example. And then there's a whole bunch of them actually. And then there's this sort of a structure next to it that looks like a honeycomb. To the left, a big structure. Right on that side of the screen.
this right here. Yeah, that's Pediastrum.
Pediastrum. Look at you.
Yeah, I remember some things. That's all the way back to lakes and wetlands a couple semesters ago.
It's a good catch. So sometimes the pediastrum will still be, it'll make it through the processing. So Synodesmus pediastrum and those are the 2 primary ones that usually make it all the way through that we learned. And there's another Navicula, I think, one of the big ones. It looks like it's a little bit cleaner. Well, Pacific Plankton's got to run. Thanks for hanging out and visiting with us, Pacific. Hopefully you'll come back and catch the second half. So this still has a bunch of clay, but that Alicocera that's above us doesn't. Or it has some, but you can kind of see the structure up there. Yeah, it's the double click to get rid of that.
Okay.
You can see more of the structure there than we could before anyhow. So middle mouse will get it to the middle of the screen. And then the top button will zoom us in. Okay. And then you can focus it.
Wrong way.
Yeah. I usually put the box up to focus just because I think it's easier than waiting for it to redraw the whole screen. But you just do whatever is comfortable. So this is
actually smarter.
Another Alicocera, so little tube-shaped things. And this one's laying on its side. And because it's laying on its side, we can probably tell both the genus and the species. I think this is Alicocera ambigua. There's 2 things that sort of lead me to that conclusion. One is that it's got a bunch of little areolae, a bunch of little holes on the stride. And the second is that there's no sulcus between the stride area, the area that has the sort of little dots on it, and then the column at the bottom of it. And if you look like inside of the diatom, you can see that there's the ledge that I was talking about. That's the ring least. And in Alicocera ambigua, the ring least is actually a little hollow tube. And You can't really see that because this one's intact. But if it were broken, it would be a little hollow tube. And you can actually see that in the light microscope better than you can see it in the scanning electron microscope, which is weird. But because the light microscope actually allows us to sort of see through things, and the SEM only allows us to see the topography, the surface structures.
Yeah.
A lot of things, you know, when you're looking at it, even though you're looking at it in something that, you know, our magnification right now is 13,000 times. So in a light microscope, our max resolution for magnification is at 1,000 times, and so even though we're looking at something like 13 times more powerful than a light microscope right now, some elements of that's actually easier to see in the light microscope. And this is one of the biggest adjustments for me when I caught the SEM, is like learning how to translate what we see in the light microscope into what we actually see in the scanning electron microscope, because it's not easy, and it takes a while to sort of adjust your thinking to like, oh, that's this thing when I see that, you know. It's like if you only saw people as skeletons your whole life, and then finally you saw people walking around, you'd be like, that's what they look like?
Yeah.
You know? So I think that's part of the thing that makes it so interesting to me. It's like you're familiar with stuff, but it doesn't matter how familiar you are with something. Seeing it in the scanning electron microscope just makes it look different.
Yeah.
Because you're not used to seeing it like it's the size of a basketball, or, you know, an airplane, or something that you can actually see, you know, details on. So. Hello, GZ Baku. How you doing? I feel like everybody should just have easy names for me. I'm just gonna call him GZ. How's it going, GZ? Everybody gets a nickname. Unless your name is nice and short and easy. Some more Criticula right there, and then that one is probably a Navicula again. The one that's to the left, or the right of that, is the Criticula. And then there's an Oligoceros sitting on top of it as well. Yeah.
And then that's a Pediastrum.
Pediastrum, yep. You're doing pretty good with those, at least.
I know those. They look like waffle cones.
You're a fan of waffle cones?
Yeah. Yeah, can't beat them. They're good.
I'm trying to think, if I was getting ice cream, would I get it in a waffle cone? Probably, unless I was counting calories, and then I'd probably just get it in a bowl. Sugar cone or a waffle cone?
Yeah. Waffle cones are great.
It's the other type of cone. I don't know, what do they call those other types of cones?
Sugar cones.
Oh no, the sugar cones are like, aren't those the ones that are like a...
Oh yeah, I guess they might be. And
There's
then
one that's like a not sugar cone.
Yeah, that they always have in the little paper.
It's like styrofoam?
Yeah.
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 They don't taste good. They only taste good after the ice cream gets inside of them.
Yeah. I just don't think there's anything better than mint chocolate chip ice cream and a waffle cone. That's about the best there is.
That's up there in my flavors for ice cream as
Yeah.
well. Mint
Love
chocolate
it.
chip is a good one. I like pistachio flavored ice cream.
Yeah, that's good too.
All the green ice creams are good ones. Green tea ice cream, still good. I can't eat green tea or drink green tea, but if you put it in ice cream, I will.
I did not know they had that.
That's actually something Carlin really likes.
Really?
Yeah, my wife. So, Addie's project that she's working on is actually one where it's a grant that my wife procured, along with Broxton Berg. So, while Addie is technically under my supervision, she's also under my wife's supervision. So.
Is this a, is that a pinnata?
Yes.
Okay. These are very common in my sample too.
It's Styrostyrella pinnata. And you can tell because it has the lineolate-like structure and striate, but it's a fregullarioid. Yeah, and that's actually a good thing to check, because I have had some samples where we thought we were looking at star Cyrella, and then we put it on the SEM, and it's like, oh, this entire time we've been thinking these are star Cyrella, but they're actually Punctus striata, you know, or something
Yeah.
that you can only see the detail on the SEM in order to figure out what it is. So,
What's happening here?
just need some focus.
Did I
Oh,
speed it
you
up?
sped it up.
Okay. How do
Yeah.
I slow it down?
If you roll the mouse wheel towards yourself, it
Okay.
slows the beam down.
Okay.
Yeah.
That caught me off guard there for a minute.
Sorry. Yeah.
Which I knew
towards
that,
The
I
screen
just-
is faster.
okay.
Towards yourself is slower.
I didn't realize I did
So
that.
when I move around, I just do it naturally. Like I spin it forward really fast,
Yeah.
and then I move around, and then I spin it slow down. So like the movements. Oh, that's a nice view of that Alicocera. It's
Oh,
mostly
yeah.
clear. You know, it's like it's like riding a motorcycle or a bicycle or something. Like it becomes an extension of your
Yeah.
mind or your will, and you don't have to think so much about it. It's actually quite a relief after a while of using it. Just like, oh, I get it now.
Yeah.
I can move all the things. I don't have to think every time I go to click something. So again, that's Alicocera ambigua. That's actually a pretty nice view of that. There's not a whole lot of junk on it. And I bet we could zoom in really close and look at the spines, so that is what you're looking at is two sister valves. So Alicocera create long colonies, and they're held together by spines that sort of knuckle together. So like if you put your fingers with your knuckles out like this, sort of interlocked, the spines function that way, and they hold the two sisters together. And I like to think of them as like they hold on so tightly they'd rather be ripped in half than actually let go of their sibling valve. So what you're seeing is one half of one diatom, a set of inner connected spines, which you've got nicely resolved on there, and then the other half of the diatom, of a different diatom.
Yeah.
So there's two half cells there. Together they would, you know, there'd be two if you were counting them for valves, or one diatom, but it's across two different valves, right?
Okay. So this isn't the same.
Nope. The cells connect on this side,
Okay.
not on that side. So the
Okay,
two
so
cells
these are
would be
two different
joined.
things.
It's two sisters.
Okay.
Right? The two sibling cells that are in a colony together, but they're half of each. So it's actually a really good thing to like get your head around before you start counting them.
Yeah.
You know, to know that the spines are the part where they're connected together.
Yeah.
And then when you see them, you'll instantly go, oh, it's got the spine, so I know that's the valve face.
Yeah.
And then the other end is got the column, so I know that that's the part where it connects to the other diatom. And it's easier to count then because you can go 1, 2. You know that that's not a cell, but two half cells or whatever, right?
Yeah.
So you can often find them still attached, but the girdle band in Alicocera wraps around the outside of it, and that actually functions to sort of hold it together. And so if the girdle band snaps off, then they're more likely to break apart at the cell.
Yeah.
So that big long thing that you're looking at is not a diatom. Do you know what that is? It's a quiz
I
from
don't.
Lakes and Wetlands again.
I should know what it is. I feel like. I think Sukanya had one of these in her samples
It
the
looks
other
like a
day.
toothpick, right?
Uh-huh.
So that is actually a sponge spicule.
Okay.
So sponges make these like needle-like structures inside that are all made out of silica, and so you have some freshwater sponges that are in the lake, and they're generating those.
Yeah.
GZ asked, can you look at microchips? We definitely can. I don't have any microchips that are exposed that I know of, but you could definitely look at microchips in a scanning electron microscope. Potato Chips says, I have fossils downstairs that look just like this, but seeing it like this is so cool. We have fossils downstairs? Downstairs? Well, these are microscopic, so unless you're looking at them on a microscope, you probably wouldn't see them. Everything that we're looking at is basically dust-sized particles, and Some of the very large ones maybe reach into the sand size, but most of them are basically silt-sized or dust-sized particles. So, you know, as clearly as you could see a speck of dust, you can see these. That is a
Is that acanthidium?
yep. It's some sort of acanthidium. It's probably actually been moved, but it used to be acanthidium exiguum.
Yeah, I think I talked about that in
Yep.
class.
Yep.
And they had like just moved it.
Zatimus says identification is the perfect task for the neural networks. And hello. Yes. So Belgianul says like a zipper. Yeah. So the diatoms that have spines are definitely kind of zippered together, and it's sort of hard to pull them apart as a result. So like a zipper or Velcro, the spines kind of link together, and then the colonies actually sort of more likely to basically stay that way. Actually, right. Can you zoom back out? You were zooming out and then you zoomed in. Right here, we can actually see the valve face of an Olicocyra, and the little spines are sticking out like directly at us. So,
Wrong way.
once we get the controls.
Yeah.
Oh, maybe it's not an Olicocyra. No, it's not an Olicocyra, but the spines are still sticking out at us. So that is probably Staroscyra. Yeah, I think it's Staroscyra. Construans or Venter, something in that neighborhood. So if you zoom in farther, don't be afraid to just get out all of its face, its valve face. And then just double click on the stri area and then use the focus wheel.
Okay.
There you go. Very good. And then double click outside the box and everything will get that focus.
Okay.
So if you click in the middle of it and move it into the center of the screen, you can zoom up even closer to it. And then what we can do for this one, if you want, we'll just take a picture of it.
Okay.
So you can see how easy it is to take a picture using the scanning electron microscope.
Okay.
So maybe get the focus perfect, yeah. And
It's right in there.
that's good. And then slow the beam down. So if you go to this speed button at the top in this column right here and change it to like 7,
Okay.
that will slow it down really good.
Okay.
And then we'll get a nice, clean, highly resolved image. And the picture button is actually that one.
It's right here?
Yep. And it takes a picture at whatever speed this SEM is set to.
Okay.
So if you set it to 10 and it scans, it'll take an hour and a half to scan the image.
Oh my
It will
goodness.
take an hour and a half long picture. So it's totally dependent on whatever speed you have it. So if you have it set on 1 and it's going to look grainy, it'll take a grainy picture. It will just snap it. It'll take a couple of seconds. So potato chips, you'd be surprised. Objectively, it looks the same. Well, I'll take your word for it. Oh, I see. You mean like you have some fossils that are similar, that are fossils. Yeah, so that's probably true. If you're looking at large-scale things in the small scale, a lot of the structures are kind of similar, and that's largely because biology, you know, there's sort of optimal shapes for things. So as someone in here mentioned, and microscale and nanoscale features sometimes get replicated at the macro scale. Yeah, so that's true, Bougie. So also, thanks for the follow, Bougie. And we got a follow from LecX287 and also BlotMath. So a couple of great new followers. Hello. So there's a question from Belgianul. Do I know how much an scanning electron microscope costs? I do, because I was intimately related in purchasing this one. So this scanning electron microscope cost us around $160,000. So, pocket change. And you can get a sort of a desktop model scanning electron microscope for probably closer to $60,000. I don't know that they come any cheaper than that for like a new one. That's kind of the range for non-field emission scanning electron microscopes is sort of like in the 60 to 200 thousand. And then if you go with the field emission microscopes, field emission scanning electron microscopes are usually starting around 200 or 250 and kind of go upward to like a $500,000 from there. And then if you want to get like an ultra high resolution, ultra fast scanning electron microscope, those are like I said, several $100,000. And if you're up there in the 300,000, 400,000 range, you might consider getting a transmission electron microscope instead of a scanning electron microscope, which functions a little bit differently and does different things. But here we just have a regular old tungsten scanning electron microscope. So, yeah. Ovi Bros gave us some prices down there. I guess they've been looking at them. Thank you for that, Ovi Bro. Yeah. You can get a whole bunch of them. I don't know how you found the prices for them. It's actually sometimes challenging to get real prices out of stuff. Sorry, this is just the notes, so we can put in that field Clear Lake. And then hit OK, and then I'm going to make a folder for you.
Okay.
That'll just be outside of this box, inside of my file, which we'll also call Clear. Sorry, reaching around in front of you to type stuff, and then we can click Open. And in here, you can just type Star Syra. And this was in 6 to 7, so you might want to put that somewhere. Yeah, perfect. Okay, well, I think I'm going to let you off the hook.
Okay.
We got a whole hour on the SEM, but we can always have you back whenever.
Yeah.
We can get some samples that'll be a little bit cleaner as well, and then put those on. We'll have plenty of time.
Yeah.
So maybe this spring we'll make it a project to have you do a couple of hours a week on the SEM, maybe.
Yeah.
If you're up for it.
I am.
Your schedule will be a little more open now.
Yeah.
Because
Hopefully.
you only have 3 classes instead of 5.
Yeah.
Or 6.
Last semester was
Yeah.
interesting.
All right.
Okay.
Well, I didn't mean you don't have to leave if you don't want to, but you can if you want to. So
I'm not.
don't feel obligated to stay. And we'll come back and look at some more Clear Lake stuff. But you're welcome to hang out.
I'll hang out. This.
Oops, I didn't mean to close that.
I think I'm at a standstill with my sampling right now.
You have to wait till stuff to process. Yeah. So I'm going to hop over to the samples that I collected from Pacific Plankton, who's one of my friends on Twitch, who sent me some material from San Francisco Bay. These were collected in early December, so this sample is really crowded. And I made some samples where I should have fixed this beam intensity earlier. You've been running on 6 the whole time. I made some samples over the weekend where we looked at some of them, and I made this sample at the same time I made the other ones, but it didn't dry completely before the stream started, so I just left it on the hot plate, warmer plate, warming, and came back to it. So we have some here. Material from that, and then I rinsed those samples some more because they had a bunch of clay on them, and I thought, I probably could get them a little bit cleaner. So I went back and rinsed them a bit, and that's what we're looking at here, is actually the sample from last week, I think, from Saturday rather, and then the ones that I made today that I rinsed again, we'll also be able to see. I think they're a little bit more sparse. So I want to play with getting the focus just right. I could have done this before I handed off the SEM to you. It probably would have helped a little. But when I get a whole bunch of little holes like this, it's actually ideal for trying to get the stigmation correct. So there's a couple of things with the scanning electron microscope that help you get a really good image. The first of these that we're going to cover right now is the wobble. So the beam wobbles a little bit, and we can adjust the wobble. And the sample looks like it's blurring, but in fact, when the wobble of the beam is aligned perfectly, what happens is the sample looks like it's just coming in and out of focus. And when it's misaligned, what happens is it moves in a direction, either up and down or left and right or into catty corner if it's both directions. And our wobble's spot on, right? It's just going in and out of focus, but the circle is staying centered. And we're zoomed in really close. That's a 1 micron field of view. So we're currently looking at 55,000 times magnification, and it's not wobbling at all, right? So there's nothing wrong with our wobble, which is good. That usually happens when I look at diatom samples, and that's the only thing I'm looking at is diatom samples because it's set from the first time that I did it. If you put some stuff with water or sort of organic components in it, in the SEM, it sometimes causes the column to get a little not cleanly aligned for the wobble. And it's actually a lot of work to get the wobble fixed so that it works right. The next thing I'm going to tweak before we go any further is the stigmation. And just like you have in your eye, you might have astigmation. The light coming in hits a lens, and then it may not land on the right spot in your eye. And so for a stigmation, what happens is I think it's set too short. No, it's set off position in either an X or a Y position. So we can move it around. We're not using light, we're using electrons, but the idea is still the same. And I wanted to, I turned the beam intensity because I'm still on beam intensity. Sorry, I thought I hit stigmation, but I was not stigmating at all. I was just tweaking the beam intensity. All right, so it's just like at the doctor's office, you tweak it until it looks better. And I just look for maximum contrast. So right there is kind of maximum contrast. And right there is sort of a maximum contrast. And then the stigmation will be nice and clean when I slow the beam down. So if I were to click in here and change the speed setting to 6, for example, you see those little tiny holes, and you can even see that they're like lunate shaped.
Yeah.
So they're pretty well resolved, and that's like that box is about 1 micron. So we're looking at things that are nanometers in size, and we're still getting pretty good resolution on them. If I wanted to make them look even better, for example, if I was going to be crazy and make this thing my whole field of view, and I'm at 160,000 times magnification at this point, I can do that. If I lower the beam intensity, they'll still look okay, probably. You know, we can still see them pretty sharply resolved, and our scale bar is 500 nanometers now, so we're looking at really small stuff. And I probably could focus it a little bit better. But if I want to get into this sort of scale, I need to get a little closer. So right now, we're at 9.9 millimeters away from the sample. If I move us down to 5 millimeters, this is always the terrifying part because that could actually break my machine. So, and I just would need to focus it a little bit at this point. So I'm going to zoom back in, slow it down a little, and then work on the focus. So we got a little bit closer. Like anything else, when you get a little closer to it, everything will look good until you get a little too close, and then it'll be blurry with your eye. But that doesn't happen with the scanning electron microscope. As we get closer, it just goes, okay. And then I can change the brightness contrast settings, and we'll be able to see those little lunate shapes in there very clearly resolved. So you can see from this scan that all of those things are still pretty sharp. And that's because we just moved a little bit closer. Actually, we about doubled the distance we had. So if I found some sort of place that's kind of doesn't have any other junk on it, and I slow the beam way down to like an 8, when it rolls across those, we'll see nice sharp lunate structures, highly resolved in here. And it just takes a little while for it to draw it. But that's how clean our image is. It's a really nice, clean image. And we're basically optimal with our stigmation, our wobble, and zoomed in, and our beam intensity's at about half of what it was. So beam intensity is the size of the beam. So I'm going to snap this photo. Actually, maybe I want to speed it up a little so I can make sure it's all there. Yeah, I'm going to snap this photo. It's going to take a little bit to draw. I think I want to maybe make this a 6 and this speed a 7. So we get a nice high resolution image, but we don't have to wait for 10 minutes for it. Or maybe I'll go with an 8, and then I can actually talk a little bit about the scanning electron microscope. Why don't I do that? Okay, so for people who don't know what a scanning electron microscope is, I'm going to spend a little bit of time talking about it. And I put some hotkeys in here. That one gets rid of me. And this one will get rid of the picture for a second, so you can kind of see what a scanning electron microscope is. At the top of a scanning electron microscope, there is an electron gun. And what it does is there's a little field in here that's being generated by tungsten. And the tungsten just gets charged up and enhanced, heated up a little bit, and it creates electrons. And they're captured inside of this, like your grandma's TV. I don't know about that. And then there's a anode that's outside. It has a positive charge, and it pulls the electrons, which have a negative charge, out of the Weinhold cap down into the chamber. And from there, they go down, and they're focused by a series of lenses. So because we're not using light, we're using electrons, you're seeing the electron beam being focused by magnets. As the magnets basically keep the beam in a nice sort of tight beam shape instead of spreading out into a cloud, and they focus it through a series of these things down onto the sample. Then the electrons beam into the sample, and some of them go penetrate into the sample, and they will knock other electrons off of the material. So there's a bunch of different ways that can happen, and I'll talk about those. And then they're collected by this thing, which is our secondary electron detector. And in here, thank you, Scotty Fox, for the follow. What happens is that each place where the electron beam hits the sample, it kicks off some electrons, and it records its position and then how many electrons it collects from that spot. And like a flashlight, if light's bouncing off of a subject, if it's angled towards you, more of the light gets to your eye, so it appears bright. And if you were looking at this side, basically you wouldn't be able to see as much of it because it's dark. So the sensor that's in the scanning electron microscope, if it's pointed towards it, it's a little bit brighter if it's pointed away from it, and that basically creates a three-dimensional image as it scans across that surface. So it's creating it from there. So what we're seeing in ours is these bright areas are a little bit closer towards the sensor, and so as a result they're getting more electrons from that spot, and then it just draws it pixel by pixel. The size of the beam is the beam intensity. Effectively, it's how big is that beam coming in. So if we had a beam intensity that's very high, it's going to make a big circle, it's going to get a lot of electrons from it, but the image won't be as clear because we're using, it's like we took and tried to draw an image with a a fine tip pen versus a Sharpie, right? So it's got a lot of bleed associated with that image. And the smaller the beam is, the tighter that image is and the higher, finer resolution we'll be able to get. But it's only moving the beam the same number of spots each time at the same speed. So when we shrink the beam down and we leave the speed the same, what happens is the dots are more widely spaced. And so it's not as good of an image. So to compensate for it, we have to slow the beam down. So the combination of making the beam smaller and then slowing it down puts more dots in it, and then we have a more highly resolved image. So just like a printer, basically, we're printing the image as we go. Thanks for the follow, OX4D _. Anyway, so I have one more graphic that I wanted to show, which is this one. And here what you can see is when the electron beam comes down and hits whatever it is that it's hitting, it interacts with it in a number of ways. What we're looking at in our image is this, the secondary electrons, which give us a topographical information. They're telling us what's on the surface and what's the shape of the surface based on how many electrons are getting back to the sensor. What people probably don't know about the electron microscope is that the beam's coming down, it's actually knocking electrons out of the material. And then they're being captured by our secondary detector, which means so electrons are coming in, they're blasting electrons out. So if I just left my beam sitting on it for a really long time, I'd actually burn a hole in my material. It'd take a long time because I'm just doing it a few electrons at a time. But you'd actually be able to like burn a hole in a sample. So this sort of really shallow surface are called Algar electrons that are, some of them actually just get reflected off of the material. Some of them will penetrate into the material and they make this sort of little globe shape in here. So they come in, they knock an electron out. And some of them come in and will penetrate a little bit more deeply. And these are called backscatter electrons. And they will actually tell us not just information about the topography of the surface, but rather also what kinds of material it's moving through, like the density of the material. And those are captured by a backscatter detector. And in ours, the backscatter detector, I don't know if you guys can see that. I don't know what you guys see when you see me moving around my mouse. But in the image above, there's a little arm off to the right that is the backscatter detector. And when that's engaged, we can actually get the density of the material. Now, for ours, we're just looking at diatoms, so it's always the same density. It's silica, and we know what the composition is. It's silica plated in gold, so we don't really have any information that that's useful. So I almost never use the backscatter detector. But if we were looking at something metallic or mineralogic that was like not just silica, the backscatter detector might be highly useful because it would give us information about differences in density of metals or differences in density of elements that are in it. So you can also get from the scanning electron microscope elemental information. And so we have in our scanning electron microscope an EDAX detector. And when the beam interacts with some of the material, it knocks electrons out of different shells of the electron. And when that happens, an electron from the outer shell comes down into a smaller shell, and when it does that, it releases a little bit of energy. And so what this electron, the EDAX detector does is it gives off that energy in the form of X-rays, and it captures the X-ray, and it sees the energy of the X-ray, and it says, oh, this is probably this element, because if I got rid of something from the S shell of this element, or the D shell of this element, or whatever shell it's in, and it moved down, it would give off this much energy. But it has to sort of guess at it, because it doesn't know for sure, because there's a whole bunch of different elements, and they all have different shells, and we could potentially get a similar signal from something like lead and gold. So it's either like, you know, the S shell of this element, or the D shell of this element, or something else. So, but it tries to estimate what it is, and we can actually get elemental information out of it as well. And there's a bunch of other things on here. You get cathodoluminescence. I don't have a cathodoluminescence sensor in mind, but this gives us electronic state information. And then there's a bunch of these other types of things that are given off. If the electron goes all the way through the material and gets captured down here underneath it, we don't have that capacity. That's a transmission electron microscope. So it's functionally like a light microscope in that the beam goes all the way through it, rather than more like ours, which functions like a stereo microscope where your light's bouncing off of the surface. So kind of neat. I thought I'd just throw those up and talk a little bit about, yeah, you can't see the mouse pointer. That's okay. So just so that we could have a little chat about how does the SEM work, I always told people, oh, I'm going to put something up one of these days about how the scanning electron microscope works, so we can talk a lot about it a little bit. But I thought I would just throw that up for people if you're interested in it. So we got some new follows. Flamed Eye, Viral Corgi, Blot Math, I guess we caught that one before, Ambrose 97, and Messing With You. Are you messing with me? Okay. So yeah, those are pretty classic slides. You can just find them. That's from, one of those was from Encyclopedia Britannica, and the other one I think is from Wikipedia or something. So pretty basic slides, but just to give you a sense of what's going on in here, right? What's going on in the machine? Why are we seeing what we're seeing? Or not really seeing, but you know, what you want to call it. So this is what we're looking at right now is a very, very close. This is a 55,000 times magnification view. This is San Francisco Bay 7. And I'm in the wrong folder, of course, because we moved yours into there. This is 7. And this is a close-up view of Asteromphalus, A-S-T-E-R-O-M, phallus, Asteromphalus. This is like we're seeing through it from the inside, so internal view of areolae. And these little things that you're seeing are part of the covering on the outside of each one of these holes. So it's a crazy view for this particular thing because we're so close you can't even tell that we were looking at, secretly there's a diatom under that weird shape that we were looking at. It's super bright now that I switched back to the beam intensity 10. So one of the things that's nice about switching to beam intensity 10, like I said, it's like, drawing with a fat Sharpie, but it actually gives more information back because there's more light or electrons hitting it in this case. Mm-hmm. So the image looks nicer when we're going fast. When we're going slow, the other one looks a little bit better. So we get a nice clean view of what we're looking at. Just this little part in here of that, this diatom, Asteromphalus. And that's what we're zoomed in 55,000 times. Right now, we're at a view that's at a magnification of about 2,500 times. So about 2.5 times as good as you could see on a light microscope, for example. And I can just do like a relatively quick shot of this. I'm going to change the beam intensity to 7 so the image just looks a little bit better. And then fix the brightness and contrast settings, and then I can kind of hop back. I've been really not talking to chat very much relative to how much I normally talk with chat. Because I was doing a bit of a mini lecture there. Just to try to give people some idea of how the scanning electron microscope works. So if you had questions for me or for Addie, I'll try to get to them. A lot of times when we run the streams from the SEM, because it kind of takes all of my attention to make the images part, as Addie can attest to, running this while talking is hard enough, but also trying to bounce over and see what chat's saying at the same time and answer questions gets a little hectic. So there's like a whole ton of these things I probably didn't address. Kevin Simulator, hello. So let's see. I'm way back here. You'll just get a house. Yeah, you could live inside the SEM if you wanted to. It's very small. I think the chamber might, if you were a cricket, might be comfortable. Anything bigger than a cricket, you probably wouldn't like living in there. Let's see. Cinnamon, hello. It's nice to see you again. Can you look at 1 nanometer? No, not on this SEM. We can look at stuff that's maybe a couple 100 nanometers and still get focus. Oh, she's the best? Oh, well, that's good to know. I'm glad. There's holes in the holes. It never ends. Yeah, that's how diatoms work. There's holes inside the holes. I agree. So let's see. I think I was looking at 2 nanometers. I don't think I can look at 2 nanometers. The beam itself is about 2 to 3 nanometers on my scanning electron microscope, so I can't get down that small. But, you know, I can get pretty small. Hundreds of nanometers is still pretty good, in my opinion. The best images that we've collected from this at that sort of scale, I've collected some that were just a little fuzzy at about 160,000 times magnification, and that sort of gets to the point where I'm tired of looking at it because it's a little fuzzy. So, but an SEM does work a lot like an old TV, similar to a CRT, where it scans across and draws the picture for you. It's the same concept. It's just, yeah, a lot more powerful. Scotty Fox says, I love this genre of content, micro and macro photography, and now this SEM. Well, I like macro photography is my favorite, and so if you wanted to see some of my actual photography that's not on a scanning electron microscope, you know, you could check out my Instagram. So Kevin Similar said the first time the magnets failed when he was using a TM, he nearly soiled himself. That sounds bad. I have a degausser. This one just degausses occasionally every time I restart it, basically. So Scotty Fox says they're a biomech engineering student, and this material is like extra content. Yeah. T-Perm says, I didn't know you could use it to look at all these things. We can put whatever we want in there as long as it fits in the chamber and it's not wet. So that's basically the limit of things. Yeah, let's see. I think I can make OBS give me a cursor that I can move around, but I haven't figured out how to do it yet. I asked Specific how she's been doing it. Yeah. You can read the energy on the computer and it can guess what it is. Yeah, that's how the EDAX system works. Sorry, I'm a little behind, so little mini lesson. Sorry about that. Can temperature make electrons change their orbits? I don't know, I'm not a chemist. You're asking highly technical questions. Okay, I'm going to jump back and do some more pictures. This is, again, Astroomphilus, and this is a sample of a diatom that we've collected from San Francisco Bay, and this is an internal view of a valve. I'm going to give it a clever name, Internal View 2. But it has a whole bunch of really cool structures. These things are called rays. The things coming off of the diatom in the middle are called rays, and they're really only common in a few types of diatoms, usually ones that start with the word aster. And then it's got one that's not the same as the rest of them. So this one has 7. One of them's not the same, and you can see inside of these little structures, these little caterpillar-like looking things are actually the rim of Portula. So rim of Portula on the inside of each ray. Pretty cool looking diatom. If we just zoom out a little bit to reasonable views, I think these things are Actinopticus, and that's a Thalassocyra, and that's a Chaetoceros with a nice internal view. We saw some of these on our stream before from the same sample. There's Datylum. Here's another Astroomphilus. Let's see. I want to find something we hadn't looked at much last time and try to zoom in on it. So I think we saw most of those things like Saturday, but we can go zoom around on this sample just a little bit. So you see how it's all kind of, there's a whole bunch of material. It's because I just put a little drop. It's like one drop of the processed material. This is as little as I could get on the slide at once. Oh, here's a cool little diatom. There's a couple of cool diatoms here. So these are the marine diatoms from San Francisco Bay, or mostly marine. And I don't study marine diatoms. So despite the fact that I'm giving you a bunch of technical names at the genus level, this isn't my specialty. So I have friends that are marine diatomists, and they're much better at this sort of thing than me. This is what used to be called Odontella over here. This one's kind of clean. We saw a bunch that were really covered with junk. but it's also hidden under a pile of other stuff. So not perfect. Here's another cool looking diatom up here. Just bits and pieces of them. I'm not sure what that is. I wish it was facing us. And then here's another one in that kind of group that make these kind of squishy jelly bean things. This is Thalassiocyra weissflogii. This is a Costinodiscus. So if none of those names sound familiar to you, it's because they're all marine genera, and we didn't cover any marine genera really. There's a couple of things that we saw that cross over between marine and freshwater. But I've been sort of learning the marine genera, and this is a fun way for me to do it. Throw them on the SEM and then just try to figure out, well, what am I looking at? It's a challenge, and I think part of my job, besides just doing science outreachy things like this, oh, that's a nice Thalassiocyra. I drew a picture of this one and I made it a sticker. See how it has these like weird little platforms around the outside edge? It's like a yellow sticker. That's that Thalassiocyra that I made. It's a pretty cool one. Or maybe, no, it's green and orange sticker that I did. It's a pretty one.
Is that one that kind of crosses over? Because I feel like
there are Thalassiocyra in freshwater. They usually like brackishy water in freshwater systems, or you can find them in purely like high salinity. I don't know what that is. That's crazy. Look at all that stuff on the valve face. I might want to just take a picture of that one and come back to it. That's a crazy looking diatom. Some things I've never seen before. So that's a diatom for sure. There's the valve face right here, and this is the side view of it. And this stuff is all coming off of the top of the valve. Looks like there's a forest on top of it, right? But it's silica. I just don't know what that is. And this is where, if I were an expert in marine diatoms, I'd probably be like, oh yeah, I know that one. I don't, though. And I'm totally okay with not knowing some things. Otherwise, I wouldn't ask for Pacific Plankton to send me marine diatom samples, because it's not stuff that I would just know. So I'm going to set it on a 7, and I'm just going to go ahead and take that picture because I think it's in focus enough. And then I can kind of see what chat's been saying. All right. Let's see. Sorry if you've been talking and I missed it. Okay. We're all keeping it going here. Good. You guys can chat amongst yourself without me when I'm not able to interact. If I were a cricket inside the EM, I could get some nice selfies. Yeah, except for the vacuum part. Everything takes place inside a vacuum, but you'd get some really nice selfies. You know, this morning I went in my basement and there was a cricket in there. Really? And I thought, I could put that in the SEM. It would look amazing. But my cat also eats the crickets, you know. When we let it into the basement, she chases them around and eats them. And I thought, well, do I want it to sacrifice it to my cat or to my SEM? Maybe next week. Maybe I can find a cricket that's not living, so I don't have to kill it in order to put it in there. Let's see. Billy Galaxy Art, hello, welcome back. And also Dangling, hello. I see you there hiding as breaded shrimp. I know who you are. What is the opposite of absolute zero? Planck temperature. Okay, cool. Hey, it's Sarah Lasaris. How you doing, Sarah? When are we doing lizard stuff? I need to know. Temperature will push electrons out of orbits. Okay. Thank you, Ovi Bros. Let's see. Crossover diatoms. Yeah, there are diatoms that can go between fresh and salty water. And they're not all limited by their tolerance for salinity. So they can live in a range of salinities oftentimes. So This stream kind of makes me go back to school. Well, I don't know when you last went to school, but we're at a school right now, so, you know, my lab happens to be in a university. That is a really crazy diatom. I don't know what it is. Something for us to look up later. Oh, you want to go to school? Oh, well, you know, you can come hang out with us. Aren't we all in the vacuum of space? Well, we do have like a thin layer of atmosphere between us and space, so technically, no. I'll be free to do lizards next week. I just need to know how to prep them. And you can bug me on Discord. Okay, good. You can never get to absolute zero. It's a law in physics. Thank you, Sean Weinberg. Let's see. Well, the picture's done, but I wanted to go through a couple more follows that we got. Meckles and Dual Lin Line Package, and Perception of Reality. So thank you guys for those follows. We appreciate that. You have a conference. Oh, okay. All right. I'm just going to... normally I give them a cool name, and I'm just going to call this one Weird Diatom. And when Pacific looks at that, she'll know. She's not a diatomist, but I've trained her to basically the point where she feels comfortable in figuring out what diatom she's looking at. And she probably has looked them up. So when she's here, she often will tell me, oh, it's that one. Because she'll remember one she saw in a book. You know, at some point, she should just go ahead and call herself a diatomist. When you get to a certain point, when you can start naming things to species or whatever. Oh, here's another one of those. That one, Odontella looking thing. The top half is clean and the bottom half is dirty. But you can see it has these little tubes coming off. And then it has these things it uses to connect to its neighbors. It's got little ocelli, little pore fields at the ends of each of those. And it exudes material out of them. So, a cool looking diatom. Let's see. Let's jump over to this. What is this? Oh, it's a Thalassocyra. And that's a Datylum. You can see they have little eyelash-like structures on the Datylum. Really cool, little spines around the outside edge. I don't even know what those spines are used for, because they're not... Again, they're not used to hold hands with another diatom, and they're too far away, because Datylum will stack up side by side like that in a colony briefly, but they're too far away to actually like be useful in any way that I can think of. It's a small quest that I'm on to try to figure out why diatoms have spines, you know, in places where they don't make any sense sometimes.
Would it be for like movement in the water column?
Oh, maybe like how they fall through the water?
Uh-huh.
Maybe. They could maybe reorient themselves based on the spines a little bit. Look, it's a Navicula hiding in our marine material. Huh? I think it's a Navicula.
It looks like one.
It's got lineolate-like striae. This is a little confusing in here. It's an internal view, and it does have lineolate striae, so looks like maybe a little Navicula. San Francisco Bay is, of course, a bay, and so there's rivers coming in, and it can carry material from both shallow water and from fresh water into the bay itself. And so you can find some random freshwater diatoms occasionally mixed in with the San Francisco Bay saltier materials. So the idea of diatoms that could cross over between salinities is, of course, kind of an interesting one. We talked about it a little bit on Saturday. I talked about how diatoms have invaded from the marine realm into the freshwater realm. So most diatoms, well, the diatoms originally evolved in the oceans and then moved into freshwater settings more than once. But for most organisms, salinity is a major barrier to migration like that. So normally you kind of have a preferred salinity, and then you stick with that salinity. You know, there's not a lot of it's hard to regulate for salinity, and so they just kind of stick with their salinity that they're dealt with, that they're used to, that they've grown accustomed to. There's another big diatom. That's an Isthmia, the genus Isthmia. And we see these all the time on Pacific Plankton Stream. So I put a link for Pacific Plankton in here. Of course, she's looking at live material, and here we're looking at material that's been processed in nitric acid, so the diatoms are all dead. But and we're just looking at their skeletons. So diatoms have a silica skeleton, and we're just basically looking at the silica part. But they have really neat, if we can see them, if they're clean enough, we can kind of get down to the really small scale again and look at some of this stuff really, really closely. So, you know, my favorite part about the SEM is that we can just kind of keep zooming in, and no matter how close we get, it's like, oh, there's still another level of this. You know, at some point we reach the end of what it can do, but I really like some of these really big diatoms because this hole on that diatom is two microns across, right? The areolae, the hole from the outside of through the outside of the diatom, and it's got a covering on it. But there are diatoms that are 2 microns across, and there are some that are skinny enough that could actually fit through. You know, if that were an open hole, could fit completely through it, which is fascinating to me. And also, Pacific Plankton brings this up pretty frequently in the streams that she does, because when we look at the whole diatom, not just like one of these little areolae, but rather the whole thing, Isthmia is one of the larger diatoms that you can have. So if I just set it so it's basically our field of view, and it's a little, you know, it's not a square shape, so it's kind of hard to get perfect with respect to its size. But if we were trying to eat this, for example, the width of my field of view right now is 288 microns. So it's a 200, almost 300 microns across, probably from here to there. You know, it's in a straight line. It's probably pretty close to 290 or 300. And there are organisms, like multicellular organisms, that would fit inside of that, right? And that's a single cell. That's one cell, a single-celled organism that makes a skeleton that's that big. So pretty neat. And stuck on the outside of it is a little diatom. This is a Catoceros, and that one's got crazy spines. The setae on that thing are ridiculous. So I thought this would be a nice little photo to take. And let me zoom in and get the focus right, and then I will zoom back out and take that photo. There we go. With the crazy spines on the Catoceros stuck on the side of a giant Isthmia. That's kind of a neat view. That is a diatom, a Benthic Diatom stuck on the outside of a Benthic Diatom. The Isthmia are too big to be plankton, probably. And also they're very heavy. So you can see some of the structure of the insides of those areolae in here. And one other thing I would note is that while we're taking this picture, you can see in here the sort of dark areas. You can actually kind of see through the skeleton of the diatom. And that's because I have the accelerating voltage set at 30. So 30 kilovolts. So I could lower the accelerating voltage down, and what it would do is it wouldn't let me see through parts of the silica that are thin. So in that figure that I made, that I showed you guys before, if you increase the accelerating voltage, it changes the depth at which this little blob of energy penetrates. And in some cases, it can go all the way through if the silica is not super thick, right? So you could actually get it to go all the way through the silica, and sometimes you can see stuff that's behind it, reflected back through and captured by the electron beam. So pretty cool. So let's see. Oh, there's having some sort of conversation about all kinds of cool stuff while we weren't listening. Can I ask you, don't you think viruses are using quantum physics to mutate? Well, I'm not, that's not something I study, so I will let chat answer it. Let's see. Could the spines help hitch a ride on something? Well, that's a good observation. Except for I think that those organisms don't ride on anything, so I don't know. Some cases it probably does, like this one. That spine seems to have helped it attach to that thing. I don't know if it's on purpose or not, though. There's some sort of biology discussion going on here, which is amazing. I'm just going to let you guys have that, because I don't have anything to weigh in on all this sort of microphysics and microbiology. It's really cool that you guys are having a whole chat without me, though, about it. Also, we got a new follow from Sean Weinberg. Thank you for the follow, Sean. And also, thanks for this interesting conversation that's going on here between you and Bougie and Scotty Fox. Okay. I would like to point out that my training is neither in physics, nor chemistry, nor biology. I'm a geologist by training, but I study ecology and paleoecology, so I don't look at things on the sort of physiological point. I mostly look at things as whole organisms that are how they function in an environment, more so than how they operate. So there's more qualified people to discuss that with you. This is a Chaetoceros attached to an isthmia. There we go. And that's got really cool little spines. Super excited about that find. One of the things that's sort of troubling about a scanning electron microscope from the point of view of the operator is you're looking through this like collection pile of stuff constantly, and finding something is sometimes challenging, or finding it more than once is kind of impossible unless it's huge. So that isthmia I'll be able to find again, but when you're looking through this, anything could be anywhere, and you could spend quite a while just sort of trying to find something if you were looking for something particular, right? If you were in here going, I want to find an Asteromphalus, or really want to see a Thalassocyra, it might be challenging to identify what you wanted to see and find it again. This is a Cerarella, I think, a little broken one. Yeah, it's a Cerarella. Circumferential raphes out here. It's lightly silicified. So remember I was talking about the accelerating voltage being at 30 and allowing us to see through things? Here's an example of that. So this Cerarella is very lightly silicified, and we can actually see, this is a girdle band from something, you can actually see it through this one, even though I told you that we're mostly looking at surface topography. When the accelerating voltage is up nice and high, you can actually see through it, right? And that's an internal view of something cool. Costinodiscus probably in the background there. It's nice to be able to see all this stuff. Here's another example. You can see that this is a Thalassocyra. There's its Rima portula. these are all strutted processes around the outside edge. That's how I knew it's a Thalassocyra. It has one Rhomboportula and a whole bunch of strutted processes that are like spine-like structures around the outside edge. But you can see through it, right? Because it's really thin. There's a bunch of Rhomboportula. That is an Actinocyclus over there. All Rhomboportula are around the outside. And there should be one little structure on the outside edge, which is the pseudonodulus, which is characteristic of that. And this is a Cyclotella striata. So you can see clearly distinct valve face. And these are the strutted processes that go around the valve margin, marginal strutted processes, right? Mm-hmm. So cool, some cool things. I know I told you I don't study this stuff, but these things I know what they are, all of them. This thing right here is not a diatom. This little star-shaped thing is a silica flagellate. That is an animal, not a plant. And this up here is a radiolarian. So that's a really cool little radiolarian skeleton. An amoeba-like organism. Again, not a plant. And some of these will eat diatoms, I believe. Not that one. It's bigger than it, but some of the smaller diatoms can be consumed by them, I think. Not a radiolarian expert.
Are all the rings
these? Those are all girdle bands, except for some of them are actually Thalassocyras.
Okay.
Yeah. A lot of these are Thalassocyra, so, or Coscinodiscus. I think that's a Coscinodiscus. So a lot of these are, that's a Coscinodiscus, that's a Thalassocyra, Actinopticus, but these are just girdle bands from any of these things. I don't know which ones are producing which thing. So, so that's a Thalassocyra. See how it has like one Rhomboportula that's big, sticking up like a, I don't know, antenna off of it, and then a bunch of little ring of Anthopodoportula. There's another one over there. There's the Rhomboportula on the inside and then on the outside. And that's that a Cyclotella striata. It's actually a really big one relative to the ones we've seen. And this little guy is one of my favorites to see in the samples. This is Skeletonema. So it's got little spines that sort of knuckle together. And this one down here, you can still see the girdle band is still present on it. And the girdle band's missing from this half. So you can see how the girdle band would hold these things together in the colony. But the spines in this case are knuckled together so tightly that they will never come undone. So you'll always find at least these together. But that's one valve's, and this is a different valve, and the other half of it is inside of there. So that's a whole valve right there. And then there's another half of a valve over here. So that's like the whole diatom with the spine sticking up in both directions, right? These are really pretty and really intricate, and the extremely complicated for being so little. So that's like 1 micron field right there. Our beam intensity is still high. So I wanted to try to just get a nice photo of this while we're here. Pacific Plankton always says these look like something out of Lord of the Rings. You know, it's got this very ornate, detailed structure to it. One of the things that's nice about the scanning electron microscope is I can rotate the stage. So if I don't like the way that it's oriented, I can reorient it a little. And it still keeps it in the field of view, which is great, because if I were trying to rotate this thing around normally, that might be really challenging. Sorry, I'm doing like 1 degree at a time till I'm happy with it. That looks good. Mostly vertical. And I sometimes get really fussy when it comes to the photography part, because I'm going to be looking at it for a while, and then I'm going to get mad if it's not perfect. So let's see, we'll do that at a 7. You can see that the girdle band down here, you see how it has little tiny openings? Those little tiny pores on them? And girdle bands are really delicate, and they wrap around. They meet right here, so one half of it meets the other half of it right here, and then they wrap around. But they wrap around the whole valve like duct tape or like a plaster cast or something like that, and they hold the insides in, but also they hold the valves together when they're connected in a colony. 6, 7? I think we'll go with the 7. It looks good. Okay, I'm just going to go ahead and take that. And then I can hop back over and see what's going on in the chat. An intense discussion about quantum physics that we missed out on. Yeah, you can see through some stuff with the SEM. Pretty weird. Alan MD is shown up. Hello, Alan. Let's see. Do you need electron-rich stains to do SEM? No. We don't see any color, so we don't need stains at all. I promised to teach you SEM. I gave a whole lecture on the SEM. It was like a half hour ago. I promise, I did. With all kinds of graphics and stuff. Yeah, Scotty told you. Right there. That's true. Let's see. Oh, my face is still covered by the microscope image? Oh yeah, I guess I should probably fix that. Sorry. See, we talked about how it worked, and then we talked about how that worked, and, we talked about it, Alan. You just, you gotta be here for the whole thing. Or you can just go back and watch it. They're recorded, right? So, you can catch it. I didn't mean to leave that off of there. But thank you for pointing it out, Buji. It's recorded. It's fine, Alan. You can catch it. We're looking at this really cool skeletonema right now. So you see how the background is like blurry, and also a little bit out here on the edges is blurry, but right in the middle is in focus. That is because we're so close that the depth of field. So like in a camera, you can change the depth of field, like how much of it is in focus at the same time. When we zoom in on really small structures, like I want to look at this sort of knuckled spines in here. So we make the working distance about 5 is where we are. It means that the amount that can be in focus at the same time also shrinks down. And so like when you have something that's very rounded like this, the outside edges look kind of blurred and artsy. Yeah. It's my artsy diatom photos. But if we really wanted to try to capture the whole thing, we could zoom out and move farther away, but then we can't see the detail. So you have to always make some sort of like, you have to compensate for that somehow. You're making some decision about whether you want the quality to be good or do you want the whole image in focus. And similarly, I'm always playing with resolution options to try to get like what's most important to me in this setting. So in the light microscope, you don't usually have those kinds of decisions to make. Colony. Because you're just stuck with one focal depth. But our light microscope in the lab actually will allow you to scan through things, and build an image from it. This is a really nice actinocyclus. So even though I didn't move very far, I feel like I could still take another photo here, because it's completely clean. Like no junk on the inside, no mud, no nothing. Also, Rimoportulas are fan-shaped in most of the actinocyclus. So they have this like fan, like they look like a, what do they call a fan that you fan yourself with?
A fan.
A fan? A trumpet? I don't know. as opposed to the electric fan. But then there's this little structure I mentioned, which is the nodulus, pseudonodulus, right here, which is also highly visible. Right there is a little pit on the surface. So I'm going to try to get this thing in focus. Oh, look at that. When you have it in focus, the thing in the background has a little, like, crenulated edge to it. Cool. So there's the pseudonodulus. It's like a little pit here and a bump on the surface. And then now the rim of portula is in focus. Oh, and the reason those look crenulated is because they are. They've got like a little sort of serrated edge on them. That's neat. I think it's because it's got cribra, like a covering over it. And maybe if I do a photo like this, if I slow it way down, we'll be able to see those. We might be able to, if they're preserved, we might be able to see the little holes on the backside. So I'm trying to adjust the contrast a little bit. Also, this is bright and that's a little dark, so I'm hoping it will balance the tone out a little. So the one thing that the SEM is really quite good at is getting the brightness contrast. Yeah, I think it's still a little too dark inside the holes to see it, but up here you can see them. Just a little bit. Let's go with a 7, and then I'll just manage. So you can see this little structure out here is the fimbria, and then there's these like crenulated surfaces on here, which is kind of cool. Okay, so I'm going to snap that, and then we'll do one with like a whole view of actinocyclus so we can get the whole image in. Okay. Let's see. Sue NTM says, why are you studying diatoms? Well, we study diatoms for a lot of things. In this case, I'm just looking at some diatoms from San Francisco Bay and collecting images for my friend, Pacific Plankton, also for educational purposes. But diatoms can be used to reconstruct all kinds of things because they have a skeleton that fossilizes and they're sensitive to environmental conditions. So we can use diatoms to reconstruct past ocean or lake conditions by looking from core material, because they're sensitive to things like salinity and temperature and pH and light, depth. And so all of those things, if there's a diatom that's sensitive to it, and we see the assemblage change through time from, say, a deep assemblage to a shallow water assemblage, then we know that something's happened with respect to the water level, for example. So we can use diatoms to reconstruct things like drought, human impacts on an environment, because they're also sensitive to nutrients. We can use them to analyze modern environments to see what sort of human impacts are having currently on a system. And I have used it for all of those purposes. A lot of my work takes place in East Africa, where I use diatoms to try to reconstruct past climates that humans evolved through. So if we want to look at, what was the climate like 100,000 years ago, we don't have a lot of tools that will let us go back that far, and diatoms are one of them. So we can actually use the lake records to give us a sense of what was going on in really deep time. And diatoms are highly sensitive. They have very short lifespans, and so they record whatever was happening sort of instantaneously in those lake environments, and then we can use that to reconstruct what was happening in the past. Because there's a link between lakes and climate, or even the ocean and climate. They can then be used to basically assess how climate's changed by looking at how the lake or the ocean has responded to those changes. The diatoms themselves are pretty useful. They generate about 1 in every 3 or 4 breaths of oxygen that we take. They're a major part of the food system, ecosystem, for basically all aquatic organisms. So fish eat them, snails eat them, everything that's basically a microscopic organism that eats algae probably eats diatoms. So in that sense, they can be highly useful. You really wish you'd taken my paleoecology class? Well, Addie was just in it. So she could either give you her notes or maybe tell you it was terrible. I don't know. I think it was fun, even though we were stuck in COVID times. I feel like the class actually went quite well. We had a really cool debate in the class. There's a bunch of really neat things that went on. So let's see, we got some new followers. G.A. Repa, LOL Life, LOL Life, and Consirin33. So thank you guys for the follow. And Pandemic Watch, hello, how are you? Yeah, some more diatoms from San Francisco Bay. Also, yeah, Happy New Year, everybody. We won't have a stream now before the end of the year, so this will be it for 2020. But we will be back on Saturday. So let's see. P-Chops, hello. I'm doing terrible with my shout-outs because my moderators are all gone, but shout out to P-Chops. P-Chops is building an underwater lair in the ocean, and he needs your money because he's only got about $3 in donations, and we need something like $4 billion to build it, and so you should consider giving him some money. Not you. You save your money. You're with me if we get the underwater lair. Actinocyclus. Internal. I could spell. Close. Okay. These are some of our marine diatom friends that would be outside of our lair if we were to have an underwater lair in the ocean. Cool. I'm going to just go straight ahead and snap that. Are diatoms classified based on the salinity of the water, as in freshwater versus seawater? Alan, that's a good question. So I taught a class to Addie in the fall. Addie's right here next to me. She's hiding over there. She's one of my students, and or rather a student from my lab. I don't own her. And we learned a bunch of freshwater diatoms. So since we're looking at marine diatoms, how many of these genera do you recognize?
Maybe 2.
Maybe 2 out of all the ones that I've shown you. So that's a pretty clear indication. So she learned all the freshwater ones in the class with me, basically, that all the common ones, and she didn't recognize any of these. That's a pretty clear distinction. So the marine stuff just looks totally different than the freshwater stuff. And the only place where you might get some confusion is that we use the word freshwater when we talk about lake systems, but sometimes lakes aren't fresh at all. Sometimes they're salty lakes, and sometimes lakes actually can be more salty than the ocean. So there are hypersaline lakes that are saltier than the ocean by a lot, like 2 to 3 times as salty as the ocean. And we would still call them freshwater, but they would be inhabited by diatoms that like really high salinity. And maybe some of these marine stuff would be found in those. But salinity is like a main barricade for diatoms for most of them. There's just a few of them that can kind of cross between readily. And mostly at the genus level. Like at the species level, there's probably still like just stuff that's marine species that you would never find in a freshwater system. Because the salinity varies too much for them. So they're what we would call stenohaline. In other words, they just like a little narrow band of salinity. where they're comfortable in it, and the rest of the time they wouldn't be comfortable at all. So Actinocyclus is one of these species that you can find in freshwater systems. The one that we're looking at right now, a genus that you might find. I found Actinocyclus normani in the Ohio River and also in Lake Superior, but I think probably they were brought in by ship ballast water, and they can just handle like, a range in salinity, so they can manage it. But generally speaking, probably most diatoms are just pretty stenohaline. They like one type or another. So we got a new follow from Ansel M. Bauer. Thank you for the follow. So we're almost there, yeah. Pretty much at the finish line of this fundraiser. Also, the fundraiser is going to include a company picnic. So once we get the underwater layer, I think we're having a company picnic on Neptune. Am I right about Neptune? I think it was Neptune. So a little bit of a boondoggle, but the good kind. So let's see. It would be cool to do an estimate archaic Arctic ice density based on freshwater, seawater. That's a thing. That is a thing people do. They look at the position of where the ice sheets have been in the ocean based on whether you get freshwater diatoms, or also because temperature is a primary control for some of them. There's diatoms that live only into the sea ice. And so they can use the boundary of where they find those diatoms in the ocean from the sediment records to get a handle on when the boundary of sea ice has changed over time. So you could, look at when was the last time that Antarctic ice was much broader, for example. Okay, let's see. So close. I just need $5 more, right? She is a graduate student though. So, brackish water near rivers and the sea. I wonder about populations inhabiting those zones. We're looking at one. This is one. This is what I was trying to say earlier. San Francisco Bay is in this environment that occasionally gets more fresh water, from streams coming into San Francisco Bay, and so it basically is at the boundary between these two. I will say though that from my perspective as a diatomist, working in a place like the Bay is the worst, because you are responsible for learning all of the freshwater diatoms and all of the marine diatoms, and then there's a certain subset of diatoms that really only like those conditions that are between there, that are like estuarian diatoms, and you need to know basically all three groups in those settings, which is torturous amount of diatoms to learn for anyone. So I'm pretty good with freshwater diatoms, and I'm garbage at marine diatoms. So you have pretty strong specializations usually associated with one type or another. Oh look, there's one of these cool, out on its own. Here's one of those Chaetoceros with the crazy spines. Look at those cool spines. Pacific's going to be mad she missed that part, but maybe she can catch it on the video on demand. Somebody asked that question, do we keep the VODs? And for these videos, the VODs are up for 2 months. So if you missed something from last week or whatever, you can always go back and watch it. And then I've also been secretly moving them off into a YouTube channel as well. So you could Google me on YouTube and probably find all of the old videos that would have been deleted by now otherwise. And also some videos where my daughter's playing Minecraft, for funsies. Let's see. Well, this one looks really muddy compared to the other ones, so maybe this is the one that was from last week. Because you can see how much more mud's on it than the one that we were on. Maybe we'll just skip that one and go to the next one over. See how clean that is? So I can actually tell based on how muddy it is. Whoa. That is another cool looking diatom. I think that is similar to the one we were looking at before. It's got these long tubes It's like a odontella-like diatom. I wish we could see it on the valve face. That is such a cool structure, but it's got little skinny, you know, elevations with the ocelli, and then it's got these long tubes coming off of the rim of portula. I feel like I should image that just for Pacific plankton, so later she can look at it and go, oh, that's probably this thing. Also, there's a silica flagellate hiding back here in the background and a costinodiscus on the bottom edge there. One of the things that happens when I get on the SEM, though, is I get really lost in time. Because you could just spend hours in here looking at this stuff. And I do. And then it's already 3:15, and I said I was going to stop at 3. So this is what happens. This is why my streams always go till at least 4. But I think if I tell people they're going to end at 3, then if I decide to end at 3, I can. Okay, comfortable with that. I'm going to snap the photo. We'll come back to that later. Okay. You feel more owned by the university than your professor. Yeah. It's Neptune. Okay, we'll have to carpool. Well, I mean, think of the carbon footprint if we all drove, right? P-chops, I mean, we got to be responsible. We definitely should carpool. Plus, if we carpool from here to Neptune, we can get on the HOV lane. Are structural changes based on the demand to maintain osmotic equilibrium? In other words, are there barriers to prevent influx of water down the concentration gradients? The barricades that you're talking about are mostly biological. So osmotic regulation for diatoms takes place at the sort of membrane level, not usually at the cell wall level. So they're related because the membrane interacts with the cell wall. But I think in the case of diatoms, they don't really build like an ultrastructure that would be like, this is the structure that makes it capable of tolerating salinity or anything like that. The structures that you're talking about are all biological. They're sort of wetware, not hardware, right? So the diatoms have to adjust to it. Oh, Pacific plankton is back. Good. Oh, see? She's answered all these things that I missed. Also, she can look at our crazy odontella-like thing and try to figure out what's going on with it. And send out shout-outs that I missed, like, here's Cyanide Teacups who's come to visit. Anything that takes hours is fascinating and perfect for Twitch. I don't know about being perfect for Twitch, but I could watch my SEM all day. And Addie's just been sitting here hanging out with us, so it must have gotten her transfixed a little bit. So, evolutionary changes when the salt levels and deep waters change because of thick ice sheets. Yeah, there's a salinity change associated with the melting, and also a ocean level change that's associated with the melting sea ice. So there's a bunch of different ways you can kind of get at that same information, and they should all point in the same direction if you're going the right way. So I want to say hello to, I know you already got a shout out to Cyanide Teacups. Cyanide Teacups bought a shirt with a diatom on it from my merchandise shop, and then she held it up for display on her stream. If you're interested in getting diatom artwork in the form of a mug or a sticker or a t-shirt, I will tell you that I take the money that I make from that and then I just give it back to my students in the form of paying for them to use the SEM whenever they want, and also buying supplies for the SEM for the stream. So none of it goes in my actual pocketbook, but I just still pay tax on it. So I just donate it. Kevin's Tech, it's going past midnight where you are. Oh man, I'm sorry if I'm keeping you up, man. But I want to say thanks for hanging out with us. Oh, we'll be disappointed if we use the Vogon's HOV lane. I heard that they were destroying Earth to build a hyperspace bypass, but it didn't happen, right? So I guess that would be disappointed because we wouldn't be able to take that one. It's a good thing I went over because you finally got out of bed. Aw. Well, we'll get another, like, probably half hour of me taking pictures of things. How would I rate you? I don't know, Alan. I don't rate people in chat rooms with respect to grades. Um, Normally, what happens is uh, I give people information, uh, and then they try to answer questions based off of the information I gave them. So, you know, I guess if you started asking questions that I'd already answered, I could rate you. I mean, in the sense that, like, you were here and then you couldn't answer them. That would be one thing. So, let's see. Also, grading, honestly, is the worst part of my job. Like, hands down, worst part. Hate it. So, here's another one of these. Another Odentella-like thing. Oh, this one's got so clean. It's so clean. And a little out of focus. Oh man, I don't think I've ever seen this closely into one of these things as we're about to go. Because it's always dirty in here. But look, they've got little pores on the inside. You knew there were going to be holes inside the holes, didn't you? You knew that was going to happen. Like, you saw me going like, oh, cool. You knew there was going to be more holes in there. And that I was going to have to zoom in and see what was going on. And then I'm just going to pull out a little bit so we can see what we're looking at. And I'm going to make it look artsy, because that's what I do here. I feel like that's going to make a good picture.
Yeah.
Look at those cool little holes inside the holes. Oh my goodness. Okay, let's do it. You get an incomplete. I like your answers, Bougie. Chat is making you stall. Is there a test? Not in my channel. There's not. You know, if you wanted to get the test version, what you do is on Monday nights or Thursday nights from Eastern time, midnight till 2, you could watch Pacific Plankton stream. And then sometimes I give like a prediction quiz and give away her channel points for people who guess the right answers. But only because I act as a moderator for her. That's like a quiz. And I could also probably teach her how to do it, or maybe Mallory or somebody here. Are there holes inside the holes? I think we're at the lowest level of holes, to be honest, right now. If we got any closer to it, well, one, I don't think my SEM would be able to pick it up. But two, I think there's a certain point where there's actually holes. Like, you know, it's got to move stuff out of there eventually, you know, in and out of the cell. So, I only ask questions and not provide the answers. I mean, it's going to probably affect your grade if you were getting one. Are there immunity specialized cells for diatoms? I don't know, Alan. There are viruses that affect diatoms. Is that what we're talking about? I don't know how they fight those, though. I mean, diatoms are single-celled, so they aren't going to have specialized cells for anything. They've only got one cell. So, but they might have some specialized, like, structure, internal wetware structure, that would allow them to fight viruses. The tryptophobia warning, I should put that just like as a default warning for my channel, because we're always going to look at stuff with more holes. And if you don't like holes, you've come to the wrong place. Also, if you like color, you've come to the wrong place, because we only have black and white. Because there's no light in the SEM. Oh, you actually have that problem, P-Chops? Why are you always hanging out here? I don't think that the diatoms are scary. Their holes are pleasant. Yeah, let's see. I provide answers that lead to more questions. Yeah. Are diatoms eukaryotes? Yes. That's it. That's an easy one. They've got a cell wall because we're looking at the cell wall, and they have a nucleus. So, let's see. For some reason, it's it's the dude from zoomed in wasp face. Okay. Asher Dell, thanks for follow. And also we got some follows from V4K, and RPG Demon. Wholeception. Okay, we've gotten to the end of this little part. I will save that as wholeception. There you go. That's for teacups. We were looking inside a little tiny part of that thing. Now we're zooming out. Oh, that's the Thalassiocera again. Look at that cool Thalassiocera with the crazy spines all around it. What can we find? Is a good question. I'm going to go to beam intensity 10. And let's see what we can find before I turn into a pumpkin. Pacific, you missed these really cool Cutaceras. We saw some really cool looking Cutaceras with like crazy spines. And not like these at all. They look like a tree growing out of there. And then we found something else that looked like it actually had trees growing out of the valve face. I don't know what that was. I've seen it before in like pictures, but couldn't place it. That's Acanthes on its side, I believe. Thalassiocera, Casinodiscus. Thalassiocera, Cutaceras, Pseudonychia. I don't know what this one is. Thalassiocera. See the ring? This one's got cool strutted processes on the valve face. Look at those cool strutted processes. Okay. So looks decent, but that's with our beam intensity 10. This is going to be a good example of how I changed the resolution when I changed the beam intensity. See how much clearer that is? So all I did was change the beam intensity. So now it's drawing with littler dots. And because they're still pretty widely spaced, those little dots are a little, it looks a little grainier, right? So the difference between 10, here it doesn't look grainy, but the resolution is lower. 7, now it's a little grainier, but the resolution's higher. And 5, now the resolution's even higher, but it's starting to get darker. And that's because they're just not getting as much energy coming off of the actual, like each component of the beam. And to compensate for it, then we just slow down the beam, and we get basically higher resolution and relatively brighter image, right? It's kind of a cool that you can see that structure so neatly. I just want to get a few more of them in my field of view if I can, because they're all crazy looking and they're pointing in like random directions. And then I will set it to 7. See how clean those look?
Mm-hmm.
Those holes just look gorgeous like that. And again, we have a hole with a bunch of little holes in it. And a nice clean structure. That's beam intensity 5. There's a little bit of like a silica overgrowth or something on them. Let's do it. Cool image. If we did have color, what would they look like? Are they generally colorful? No. They're made out of opaline silica. So diatoms look like glass. And they wouldn't have much color at all. They'd be translucent or transparent in some cases. And unless I played with the light, you know, if we did have light, they would just look see-through. But in order to be on the scanning electron microscope, we had to coat them in gold. So they would all be the same color, which is like opaline silica with a layer of gold on them. So not super exciting. It's a good question, F and HC. So my fossilized diatoms in a bag are grayish to white. Yeah. When you see diatomite or diatomaceous earth that you buy from a hardware or whatever, a bag of diatoms, billions of diatoms that you can buy for $5, they are they're going to have sort of a chalky color to them, probably, like look whitish, because if you get enough of them together, they refract the light and make it look white. But they're actually translucent, so. Yeah, eukaryotic, cell-walled, cell membrane, and unicellular. Yeah. Family responsibilities. Yeah. What's going on there? Why did you lose your first for a second? It's a pretty cool image. They're colorful because I color them in Photoshop. So all the images that you see that are in the bottom right corner are colored. Oh, in real life, when they're living, they're going to have chloroplasts. And so they're going to look kind of like a murky gold color, like an orangish gold color, or greenish gold. And that's where they get their name from, golden brown algae. So the chloroplasts and their pigments, actually, when they're living, if there's enough of it, you can actually see the chloroplasts. You know, like in a microscope, you could see the chloroplasts, and they would look kind of orange or brown. A little bit darker than this, you know, orange. So for the living organisms, yeah, the cell wall would still look transparent or translucent, but the chloroplasts would have pigmentation because they need to collect light. Yeah. If you want to see living diatoms, you should come to Pacific Plankton Stream, because she actually puts them on there while they're still living, and looks at living stuff. And step one for me is kill everything in the slide. So, or if it's not already dead, it will be after I start looking at it. So. Also, I'm putting it into a vacuum and coating it in gold, so it wasn't going to last very long, even if it was alive. But we do sometimes look at stuff in the light microscope, so I sometimes put live diatoms on my field of view as well. It's just, those are like the night streams from home, rather than these sort of streams during the day. Oh, I'm not sure what that is. It's got cool connectors. Valve face connectors are really interesting. Maybe Melisira? Yeah, I think it's a Melisira. I think it's got like a web structure, almost. and that's not even with the good beam intensity. I'm going with Melisira, which is also a diatom that can occur in fresh water, but there's a whole bunch of them in the marine realm that are very different looking. I need Anna to come visit and tell us what that is, because I have no idea, but I think it's Melisira. Melisira in freshwater systems are usually specialists for flowing water. So I think they're probably here flowing into the bay as well. It's 3:35. I know. In Exit U, I do whatever, you know. I lost my whole day to the SCM already. Why not just make it a whole day? Also, you know, Addie's here. She doesn't get to see the SCM and working very frequently. She hasn't gotten bored with it yet. You think maybe it's Leptocylindricus? I don't know where Anna is. I think she works during the week. So I try not to bug her, you know. She's actually doing her job and stuff. We sent her a Christmas card, and she told me she'd never gotten a Christmas card before. Can you believe that? She's like my age, and she's never had a Christmas card her whole life.
Wow.
That's a cool looking diatom, though. I still think it's a Melisira. Well, we should do a bet, and then when I talk to Anna, we'll see who wins. And then the winner, I guess, gets an award for being right. I know, it's a cool looking diatom though, right? It's got really cool little spines coming off of it, and it's got this sort of like networky thing. What are the flakes? The flakes on the left side are clay. There's a little bit of clay in the sample still. I rinsed it two or three more times today. And you can see how much clearer these were than the ones that we looked at on Saturday. But there's still some clay. So I never put it into the sonicator. But even when I rinsed it, I let it settle for about 10 minutes. And there was still clay in the water column above the diatoms. So, it was either 2 rinses and they all get mounted and we get to see them, or it was going to be like 5 rinses perfectly clean, and then we wouldn't get them actually in time for the SEM stream. So I might try to do some more rinses again. Yeah, the scale is pretty amazing, isn't it? I mean, I think she knows people know her. She said, like, her grandparents would get Christmas cards. They just don't do that because she's Russian, I guess. So, I don't know. But I told her we were happy to... Maybe. Melisira, maybe. We're happy to have been the first people to give her Christmas cards. Guitasaurus. What could we find? One more really cool thing, maybe? Maybe 2. There's still a whole nother stub we didn't visit, so... I really want to see another one of those giant Christmas tree-like things. Those were cool. Some of the stuff's just still coated with clay. Some of those might also be fish turds, or whatever, zooplankton turds. That one looks like it is for sure. Doesn't that look like a turd? That is Ellerbeckia. That's a stack right there. And on the valve face, they have these poker chip structures right there. It goes around. So that's a pretty good view. It's Ellerbeckia's soul, probably. You can see the structure on the inside of the diatom, and then these little sort of poker chip things that act as spines, again, that hold the valve faces together. That one's not particularly good for us to see the detail, because we got the inside view of one and then a broken piece of it. So another one of those Odentella thingies. That is my technical term, thingy, when I don't know what something's called. Something in here. That is an acanthidium on its side again, I believe. That's the whole cell. No, it's one cell, one valve. Girdle bands. It's a Cosinodiscus. Probably Perforatus. We see a bunch of those. I need to update my slideshow. That's what I'm going to work on next time. For next time, because I got a bunch of really cool new images, and I haven't updated the slideshow in a long time. So the little slideshow that runs at the bottom of the screen, should be a whole bunch of cool stuff on there next time, hopefully. I know all these. There's an isthmia again. There's a really long chain. I'm not sure what that is. Oh, maybe it's not diatom, I don't know. I'm not sure what that is. Some radiolarian. Let's jump over and look at this last stub a little bit. See if it's got anything good right obvious. It's an external view of Asteromphalus. You can see we started with a nice view of one of those. Here's the rays. You can see that they end up basically as little, here's the openings at the end of each one of them. And they end up with this sort of like bulbed out surface structure, which is pretty cool. There's a nice Thalassocyra, big and flat. bunch of really clean images of the diatoms, so I like that. Everything's still could have a little less clay on it, but it's better than what we were looking at last time. What is this? Just Thalassocyra. When in doubt, it's usually Thalassocyra. For the marine stuff, it's everywhere. Oh. Is it Corytheron? I bet Pacific Plankton will know this one. I think it's Corytheron. Look at those like rays coming off of it and how crazy long they are. Let's see. Set that one to 7 and take a picture, and then I'll see. She probably knows it. Let's see. How wide across is the whole sample? So Buji, one of those little stubs is 9.5 millimeters. So the whole stub, which is, let's see. You can see one of them right there. Actually, you can see 6 of them. That surface, the rounded surface of that metal cylinder, is the whole sample, and it is 9.5 millimeters in width. Any individual picture will tell you the width of the picture. So like if you're looking at a picture in the bottom corner when it finishes drawing it, when it gets close to the end of a photo, you'll see the width, the field of view width, and for any given picture it's different. For the current one that we're looking at, the field of view is 209 microns. So just as an example. Yeah, stubs for days. Do you ever mess around with radiolaria? No. But I can take some pictures of them if you'd like. But I don't really work in the marine realm. So there are some radiolaria in here, yeah. Use a scanning tunneling microscope. Evolve. No. Let's see. Diatom with 6 noses. The thing that looks like a star is Asteromphalus. Asteromphalus. Oh, I guess it depends on which one you're talking about. This one looks like a star on the valve face. The one that's shaped like a star is different, but I think maybe this is Corytheron. It has those really long, like radiating spines all coming out, and the spines have those really jaggedy edges that look like they're setae from the Chaetoceros, so they look pretty closely related to Chaetoceros. That's a good one. I'm going to call it Corytheron, and if I'm wrong, no one will know. because you're not, none of you are marine diatomists. Right? Erythron. Later on, Pacific Plankton can correct me, and then... Okay. Well, that's a cool one. I'm excited to see that. I don't think we've seen those before in any of the streams that Pacific has been doing. Here is a Rhizoselenia, the really wide one, and the girdle band structure is visible. And I've got some bad news for people who don't like holes. It's all holes. That's a diatom. Rhizoselenia, I believe. It's coming to a single point. And it just looks like otherwise a giant umbrella or something. Normally, the other end of the valve, so you'd have a long, skinny set of girdle bands overlapping, and then the other end of the valve would look like that. So they kind of look like a pen with two ends. Two pens on it. Two tips on it. And that's a sponge spicule. Here's another sponge spicule in here. That's a Pleurocyra. Oh, here's that cool Chitoceras we saw. This one has clay all over it, but look at these crazy things it has. I don't know what's going on there. I wanted to find one that was clean. That one's dirty. Alright, just one picture and then we'll call it a day. A good day, fortunately. And maybe this top-down view of the Diatom. So if it's got clay on it, would have been a good one. It would have been nice. Look how big that is. We've been seeing, oh, maybe I'll do like a family portrait style. Zoom out. Because we've got Actinopithecus, we've got this little Thalassocyra, internal views. If I move down here a little bit, we've got a bunch of really cool stuff in our field of view all together. Let's see. Put that there, and that there, and adjust this. I'm not sure what this thing is. It's like a broken piece of something. But there's a little silica flagella right there. Hiding in our plain sight. Okay. Good. Alright, I'm going to set that to speed 8. I'm going to just go ahead and take a picture. And that'll take about 10 minutes to finish. And then, hey, Dr. Javasaurus, how you doing? Haven't seen you on here in a while. Neocapitrella, yeah. Yeah. Are these fossils or are they freshly dispatched? These were collected in the second week of December. So, and they were sent to me by Pacific Plankton, so they're fresh. She captured them with a net from a pier near the San Francisco Bay Bridge, Golden Gate Bridge. Okay. How are you guys? First off, Happy New Year wishes to all of you. Happy New Year to you, Dr. Javasaurus. Look at the little ditilum next to it. Yeah, it's like a little one and a giant one. Yeah. How did I get into diatoms? I've never heard of them before your stream. I was looking for something to study for my PhD that was in freshwater systems that could be useful for reconstructing paleoclimate. And my options were pollen, which you have to process using hydrofluoric acid. I don't want to touch or be anywhere near hydrofluoric acid because it could kill you. So I said no to that. Plus, they don't look very cool most of the time, although in the SEM they do. Or ostracods, which I thought about doing, or some of the other rare things that are basically chemistry based. But I wanted something that was biological because I was kind of like into the ecological aspect of it. And so diatoms are right in that sweet spot where they're charismatically appealing to look at. They preserve well. They're basically a perfect tool for reconstructing climate and ecology of past systems. And I talked to my friend who was a diatomist at the time about them, and she showed me a whole bunch of them, and basically I thought, this is kind of cool, I should do this. So and then I started doing my PhD. I worked with world famous diatomist Sherry Fritz, who was a pioneer for a lot of diatom paleoecological studies, and I did that at University of Nebraska starting in 2000. So I've been looking at diatoms for 20 years now. Never looked back, never had any regrets about it. It's they're fascinating, they're fun to look at, and I've also become a bit of a taxonomist since then, so I kind of do a bunch of different things. It's never boring, and that's what I like about them. So if you're interested in diatoms and you want to learn more, I made a little command for that. Look at it. And you could go to diatoms.org, which is run by some friends of mine who are also taxonomists, and learn all about diatoms. So I took my first step today. I sent an email to Museum of Natural History in Belgium to ask if there are other research groups active in paleo bioinformatics. If I'm the only one. Well, we'll find out. Good luck. Okay, so we're at the end, or what I hope is the end of our stream, and I'm going to find someone to raid because we're at the end of our stream. That's what I like to do. And I don't know, my options are kind of limited because it's middle of the day and it's the day before New Year's Eve. So let's see. Well, I'll take any recommendations people have. You glad you got to see some live for the last time in 2020? Yeah, no problem. Thanks for visiting us again. Buji, thanks for hanging out with us. And there was lots of really cool discussions today in the chat. And we have a bunch of followers. Been really lucky recently with a lot of really good sort of interactions. And Addie got to run the SEM for a bit and got to see it in operation. Got to hopefully see what I was doing with the controls enough that you could kind of get a good sense of it. And we'll be able to sort of probably share some more of her getting research done this semester as in the spring as we go forward. So that'll be nice. This is my last stream of the year from the SEM. It's possible that I might stream from the light microscope. I collected a bunch of sticks and I have a bunch of water bears waiting for me to look at them at home, but I won't be doing anything else from the SEM this year in the next day and a half. So yeah, this will be the last. Let's see, what do we got? Why don't we raid Squilky? Because we haven't raided her before, and she sometimes comes and hangs out in our channel. And you love water bears? Well, I do sometimes stream water bears and diatoms from my light microscope. So raid, and I gotta remember how to spell her name. Squill, K-I-E. Just like it sounds. Squilky. misspelled it. And I think she does pottery. So it'll be sort of an artsy stream. Sometimes they just hang out and chat. But it'd be nice to give her a big raid. So I want to thank everybody for hanging out with us. And also for this year, we started streaming late in July or early in August. And we've got almost 900 followers in like half a year. So that's been pretty impressive to me. It's been great to see all the people that we've built in our community here and on Discord. And I'm looking forward to seeing what happens this coming year with the Twitch stream. So hopefully lots of good science and lots of cool things to see, and lots of people to come by and learn cool things from us. So we're going to head off to see Skokie, and I want to thank everybody, and especially thank Addie for hanging out with us today and donating some time and her samples. So, and also for running the SEM and chatting with our channel for a while. Okay, everybody, it's been fun, and we'll catch you in either 2021 or maybe right here at the end of 2020. Bye.